So because we have joined and nobody is joining, we should postpone the class. You know the class starts at 7. It is almost 7:30. Because of that, do you know that we have something doing? Because of that, we should postpone the class or we shouldn't do it at all. Why? How can you say that? Eh?
Please,
When we
it's
are
my
almost
suggestion. Please be careful. It's my suggestion that, excuse me, we should wait for them for a while. I don't know. It's my suggestion. But if I said it, it doesn't mean that we should postpone. I'm suggesting. But you are also suggesting, please be careful.
Rabbi, please, I think we should continue, please. Because waiting for them.
Please, anytime you have please mind the way, because you are suggesting, I'm also suggesting. So don't take it personal.
I'm done with your own. I've accepted your own. I wasn't referring to you. I was talking to Sarah. You have done passing your comment. I'm cool with it. I'm suggesting to Sarah that we should go on.
Look at this.
Finish. So please. I'm not referring to you.
Anytime, let us have freedom to talk of talking. That's why most of us don't want to. Please, if any suggestion, then we take the right one. That's all.
And did I attack you? What is your problem? I didn't attack you. I'm referring to Sarah that since we are done.
You attack. Don't change your destiny. You attack.
That what?
Look at this.
Guys, Mr. George Ellen Solomon, please. Saraba is on he has come back, so let's allow him.
So you take everything personal here, right?
It's okay, boss. Oh, let's continue, eh? Mr. Ravi, please, can we start, or what do you think?
Yeah, let's start. I was about starting and my network jumped. Sorry. In the house and I'm doing the class, so I'm just hoping that the internet will not disappoint me. Okay, so yes. So I'm still combining my class and Dr. Charles' class. So we are doing UCC Center and online. And we are using the model as we said the last time. So today I'm just hoping that I can cover half of the book because this is our second time. So at least if I remember, last week we did all of these ones. We did waves, we did simple harmonic motion, we did electromagnetic waves. We dived into the different radiations, their importance, their usage, which of course we've done it before. So we still did it anyways. We went to light interaction with matter. Is that okay? And under that we mentioned the law, which we'll be tackling them individually. So if you remember, we mentioned something like the reflection, the refraction, the superposition of also waves, which of course interference comes into mind. So we've done all these things. We spoke about waves, the properties, the importance. We spoke about simple harmonic motion, sinusoidal waves. We went to phase difference, which is very important because interference is mostly dependent on phase difference, because when it shifts, we want to know whether we are having a constructive interference or destructive interference, because we can think about it in a perspective like this. I want to show you something. Very good. Perspective like this. Is that okay? So something like this, we see they are in phase. And if we are to add these two together, it means we are causing something like a constructive interference. But if they are out of phase, when we say we are causing something like destructive interference, is that okay? So something like this is out of phase, but still we have it crisscross, so it will be constructive. And we spoke about electromagnetic radiation. We look at different radiations. This thing particularly, we've done it before, but I still went through with you, because if we're talking about electromagnetic radiation, we are very, very, very interested in properties like the energy, properties like the frequency, property like wavelength. And I told you that they all have a way that they all relate. Is that okay? Where we have a formula like E equals HF. Is that okay? Which we can substitute it as E equals H the speed divided by the velocity. So which means that anytime, of course, I have energy, frequency, and energy increases, it means frequency to increase. But anytime I have energy and I'm relating it with wavelength, of course, if energy increases, wavelength reduces. The same way, if frequency increases, frequency increases, wavelength also what reduces. Is that okay? Which is very, very important in electromagnetic spectrum, because that is one of the basic ways of categorizing or describing electromagnetic spectrum, depending on their energy, depending on their frequency, depending on their wavelength. So you're supposed to know all these things. Is that okay? And we dive into their individual ones and also some importance of these individual ones. And I spoke about the absorption and the emission spectrum. And I told you that we have some gas in the sky, or let's say there's even gas anywhere, and we have a continuous spectrum like this. It passes through this. This gas has the ability to absorb some of these wavelengths. Is that okay? So at the end of the day, if you want to measure the absorption spectrum, this is how it's going to be. It's not only like this, but it's just an example. Each gas has its own representative. Is that okay? So something like this, it means that the black part is where the wavelength has been absorbed by the gas. And when we have something like this, it means after the absorption, there was a re-emission. Is that okay? And now we have an emission line spectrum like this. We spoke about X-rays, gamma rays, and we jumped on straight to light matter interaction, or interaction of light waves. And we said that anytime light, of course, interacts with any matter, these are one of most important properties that we can think of. We can think about reflection, we can think about refraction, we can think about interference, diffraction, absorption, and scattering. Is that okay? Of course, we can think about all these ones. And according to our book, we're supposed to go through all of them. Is that okay? And I think as of now, we've gone through the reflection, we've gone through the refraction, and now I think Unit 2 is about interference, then Unit 4 is about light matter, then Unit 5 is about, I think, diffraction, and I think Unit 6 is about scattering and absorption, I think. So we'll go through all of them individually. So we spoke about reflection, which we are all very familiar with. The laws of the reflection. We spoke about the types of reflection. Depending on the surface, something can happen, the regular and the irregular. We spoke about another property as refraction. And I told you that Snell did a very wonderful observation where when light is in air, the speed that it will use to travel is different from when it's underwater. Is that okay? So there was a big conspiracy, what is actually going on there. And from there, we brought a phenomenon called the refraction. And refraction has actually done a lot of work. I told you, we are communicating because of refraction. And under refraction, we have something like the total internal reflection. And that is how we are able to communicate. And in fact, we have a lot of refractive indices formula under refraction, which is very important. So one particular formula is the speed of light in air and speed of light in a medium. And of course, this particular refractive index actually describe how fast or how slow a light can move. Exactly, because if I have the speed here, I write it here, and I have the speed in water, I write it here. I divide and I get something like 1.5. I'll know that okay, it's actually slower as compared to, because if it travels normal, so I'm supposed to get like 1. So if I'm getting any value, it means it's of course traveling slower in the medium. Now, there's another thing that we also look at, that is the total internal reflection. And I told you the application of this total internal reflection, which is very important, especially in telecommunication, especially in research field. Is that okay? And there's another formula too that we deduced here, comparing the refractive index to critical angle. And straight away, we jumped onto interference, a brief description of interference. And I told you that we can actually observe these wonderful colors because of interference. And I'm hoping that at the end of the class, you should be able to explain very well what is actually going on here. Is that okay? That is what we'll be doing today. And I told you we have something like a constructive and destructive. And anytime we have a wave like this, this kind of a wave is a transverse wave, right? It has a crest and it has a trough. Is that okay? So anytime we have a wave like this, we expect that if we add these two waves, we should get a bigger one as compared to the previous one. Most of the times you call this one the secondary wave. So this here and this here is merged together. The amplitude is added up. So it grows bigger. Is that okay? This end here is added. This end here is added. This end here, this end is added. Is that okay? But in a situation where there's a phase shift compared to the first wave, so you see this one, there's a phase shift of about 180 degrees. So here where we have the crest, we have the trough. Where we have the trough, we have the crest. Where we have the crest, we have the trough in that manner. And if we are to add this kind of a wave, we're supposed to get something called a destructive. It means it's a straight line. It cancels out. Is that okay? And we also spoke about diffraction. Diffraction basically is when light enters through a small medium, and because it's actually hitting a small aperture, there's something that goes on because the wavefront produces another wavefront and with another wavefront. We may imagine that if light passes, we should go straight as we know as rectilinear propagation of light, but there's more to what is actually going on, which we'll be also looking at. There's also absorption and scattering, and I told you that it's like a foam. You get the foam, it can soak a lot of water, and we have some particular materials too. It can also, you put water on it, it will just allow it to move beside it or something. Is that okay? That is where absorption and scattering comes into place. So when light actually hits on a matter, a lot of things do happen depending on the property of the material. Some material, of course, will let light pass through. Some material, of course, will cause diffraction. Some material, of course, will cause refraction. Some material, of course, will cause scattering. Some material, of course, will cause reflection. And some material will cause absorption, which is very important to know. And I told you last week that we able to see some particular colors is because of these phenomena. Is that okay? Because of something called scattering. Because our eye, as humans, doesn't produce its own light. Is that okay? It's not like something like a phone camera. A phone camera can produce its own light. So even in darkness, it can still get you a pictorial view of what is going on somewhere. The moon cannot produce its own light. So supposing there is no moon, and say it is at night, and the earth has moved to the extent that Ghana is not facing the sun, or it's not relatively a small proportion to even to the sun, it means we get a total darkness unless we have artificial light. Is that okay? We get a total darkness, but because of the reflection that we get from the moon, at least at dark or in the night, we still have some light there. Is that okay? At least we have some reflection from it. The same way the eye behaves. The eye behaves because of reflection. So light hits on something, it reflects and the eye detects it. Exactly. So I told you, we able to see some colors is because of that reflection that is going on. So we see green because of that reflection. We see yellow because of that reflection. We see brown because of that reflection. And of course, the white light that you have in your house or anywhere that you are, it has a broad spectrum, one way or the other. When I say that, I mean it has a red, it has a yellow, it has a green, all colors that you can think of. Is that okay? So that kind of light, if you disperse it, you're supposed to get all these ones. But this kind of light too, when it reflects on the sample, how it behaves tells us what is going on in the sample there. So supposing I see white as white, it means the white light is actually reflected all the spectrum. The material reflected all the white spectrum, exactly. If I see it as black, it means the material actually absorbed everything. I see it as red, it means the material actually what? absorbed everything and reflected only the red. So I can see it as red. So you can see the plants around you as green because the material as a leaf is absorbing all the white spectrum, which you know that comprises of a lot of colors, and reflecting only the green for your eye to detect. Is that okay? So that is how this thing works. And we spoke about Fermat, and I gave a very simple scenario when it comes to Fermat's principle, where we are trying to use the shortest distance to achieve what we want to do, which he used this ideology to prove for reflection and refraction. And I don't know whether we had time to go through because I asked you to do that. We went through all these things, and I asked you to also try for the refraction and see what you get. Then this man also came in, so the hygiene construction, which we will be seeing very soon. So a Dutch physicist, and he was also talking about the fact that if we have a point of a wavelength, it produces another one, it produces another one, it produces another one. Is that okay? So our wavelength that we are talking about here is just the fact that, like, when a stable water is there, and of course you touch the middle, you see the ripples that is actually generated around it. Is that okay? That is what we are interested in. And now, these things produces a secondary one, and another one is produced, another one is produced, another one is produced. Hygiene was actually trying to explain with his construction as well. Now, we also spoke about superposition of waves, which we are ideally talking about the resultant of two waves. So supposing I have so that this is the definition. So the resultant wave is the algebraic sum of the individual waves. So I have a wave like this, and I have another wave. And when I add them together, what is actually going on? What will be my final resource exactly? And it's interrelated when we are talking about interference too, exactly. So the same as I explained. If I have this, I have this, I add, I'm getting this. If I add, I'm getting this. Of course, if I had a crest, I'm getting a big crest. Is that okay? Now, let's look at something here. I think this is where we ended the last time. Now, let's look at something here. Supposing, still under the superposition of waves, I have two waveforms as this. And I'm expecting that the resultant wave, the resultant amplitude is supposed to give me this whole thing. Is that okay? And of course, the angle between the two faces should also be, give me this. But I think I added a few slides for us to understand what is actually going on. So before I go on to this week's one, any question from last week's lecture before I go on?
Hello,
Okay. So apart from Sir George, yes, do you want to add something?
Yes, the previous one, I don't know. The one you said is that 66. Who, I don't know his name, the hygiene construction.
Yeah. This one I'll be explaining it later with the principle, so maybe you understand it very well then. He will surface again in a later slide.
No problem. Then we can go on. Thank you.
But anyways, you can ask if it's something that I can just address right now, then I'll address.
No, I don't understand the concept. Things you said you talk about it. So that I will not
Okay. So
talk about it. Thank you.
okay. So
Maybe
basically,
when I
don't worry, let me explain it. Maybe let me tell you this. If a wave is generated, there's something we call a response. The wave that is generated in front is okay. Anytime this is generated, there's another form of a waveform that is also generated again afterwards. Is that okay? And this is from the previous one. So he was saying that anytime we have a waveform, there's a secondary wave that is generated, and that is from the previous one. And the new one also are giving birth to different waves as we go on. Is that okay? So he was relating the wave front in such a way that we producing a successive ones of waves out to the previous one that is actually there. Is that okay? So,
So I think you can go on. My network was breaking, so I don't know. I don't want to, because of me, will not proceed. Not proceed the lesson. So, chance we'll see. We'll meet it again. Can go on. Thank you.
Okay. So it is important that we also know how these formulas were actually generated. Is that okay? Because superimposition is basically saying that if I have two waves as y1 and y2, and we know our wave formula to be amplitude sine of our angular frequency multiplying the time minus our is okay. The same way we have a second one. Here we didn't consider is okay because we are just interested in in the time. Is that okay? We are just interested in the phases, their shift movement. We are not interested in say their vertical amplitude or something. Is that okay? So that one is ignored. So we are just going to consider these two waves. And since superimposition is telling us that for a particular waves, we want to find the resultant, the algebraic sum of the two. It means in total we want to find y equals y1 plus y2. Okay, that is what we want to do. And if we do that, of course, we are going to get y equals, this is our y1 and this is our y2. We want to add the two of them. In simple terms, which I didn't elaborate on last week, we had a resultant amplitude, that is a big A, to be equals to the first amplitude squared, the second amplitude squared, the 2A1, A2, that is first amplitude, second amplitude, cos into brackets our first phase and minus the second phase. Is that okay? So this is from the first wave, and this one is the second wave. Is that okay? So I added a few slides just to explain that. Now, again, of course, expatiate the individual waves. And if you want to expand it in a formula like trig, using trig normal rule, anytime we have A, or anytime we have, let's say, a sign A minus B, it means we say sine A cos B minus A cos B. So I'm repeating. When we have a sign like this, you see this is a sign into brackets, two individual terms here. The sign here is supposed to take this first term, and the cos will take the second term. The sign will take this term again, and the cos will also take this term again. Is that okay? So that is why we have a sign taking our angular, is that okay? Multiplying the time, and the cos come in to take this one, the alpha one, is that okay? Minus cos of the first term, sine of the second term. Is that okay? So y1 is expanded to get this whole term that we have here. And the y2 is still the same. Is that okay? So if you've forgotten your trick rules, you just do a simple revision for you to follow up. Is that okay? So, and the y2 is going to be 2 into bracket sine our first term cos second term minus cos first term sine second term. Is that okay? So when we expatiate these two, this is what we're going to get. But for our resultant wave, we are interested in adding y1 and y2. So our resultant wave is going to be y in total. Now I'm going to add this whole term with this whole term that we have here. Is that okay? Now let's look at something. If we add and do a resubstitution, or change, bring something out, we're supposed to get this whole term that we have here. Is that okay? Because as far as we have assign our angular frequency and that sign of angular frequency, we can substitute it out. As far as we have a cos angular frequency and we have a cos angular frequency in time, we can also substitute this one out. Is that okay? So that we have common terms that is in the brackets here. Now, please, if you don't understand anything, kindly feel free to stop me. Is that okay? Now, if we do this, we want to actually compare it with a total, of course, resultant of a wave. Because if we say our y is a resultant wave, we can also replace it by another waveform. Is that okay? And we can expand only this term to get what we have here. I told you that if you have a sign in trig, if you have a term like this, the sign will take the first term, a cos coming to the second term, as we have here, and the sign again will take this term, and the cos will come and take the first term. That is what we have again. Yes, okay. Now we want to compare the total one that we have here and compare to our new generated resultant wave equation. Is that okay? If we do that, it means that, of course, y is equal to this whole term. And we have a sign here, which is going to be equal to this whole term. Is that okay? And again, our cos here, a cos theta here, is going to represent this whole term that we have in the bracket. And that is what I've written here. Is that okay? Now, when we look at something like this, comparing the last term, now when you compare the last term, cos angular frequency multiplying the time was substituted out. Is that okay? So maybe they cancel each other, and then the rest of the term that is rest will be compared. That is the a sine theta will be compared to this whole term that we have in the brackets here. Is that okay? And that is what I've written down here. So now we've resubstituted, and the reason why we are doing this is for us to get the resultant amplitude. Is that okay? So that is why we are doing this. Now, if we want to find the resultant amplitude, we can add this term, and of course this term. Is that okay? We can add a cos theta as a sine theta. And of course, if we do that, it means that we have to also combine this whole thing here. Is that okay? So we can add them and of course square them. So now it's a cos theta plus a sine theta all squared. And that is what I've written here. We can substitute the a squared out, then we get cos 2 theta plus sine 2 theta. Is that okay? To be equals to all the terms that we've added squared. Now, again, in trig, if you have cos squared theta plus sine squared theta, it's represented as 1. Is that okay? So it means all this thing can be slashed out to get only a squared. And if we have terms like this, we can resubstitute the a1 squared out so that we get a term like this. And I told you earlier that a term like this can be 1 if they have the same alpha 1, alpha r1, and they are squared of a cos and there is a squared of a sine. This term can also go as 1. The second term too can also go as 1, and this last term remains because it's not represented as what we are talking about. Is that okay? So at the end, we slash this 1, 1, we slash this 1, 1, then we get a squared to be equal to, we get a squared. I remove the squared here to make it a square root. Is that okay? So by at least a squared equals a1 squared, that is our first amplitude, our second amplitude squared, plus 2a1, a2, plus into brackets, our phases, that is alpha 1 plus alpha 2. Is that okay? Here is squared, so we just square root both sides so that the square root comes here, and that is all. Now, if we are interested in the angles between them, you know that for, of course, for tan, it means we have our sine over a cos. Is that okay? And here, our a sine theta has a representation already. Yes, it's a sine theta. Is that okay? And our a cos theta already too has a representation. So we can just bring in our a sine theta, this whole thing in, and our a cos theta, this whole thing in. And here, if you leave it like this, it's very fine. Please, are we okay? Should I go on? You can give me a thumbs up if you're okay. Okay.
Master, Rabbi,
Now,
hello.
yes, is someone say something? Yes, I'm listening.
Yeah, the other calculation, the other one that you're
Okay.
comparing, like, no, the other one. This one, it's not that clear. The other one, the brown background is making the thing not clear.
This one.
No, 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 the other one, the traffic background color. No,
I don't know the
go for it.
brand back.
Go for it.
I should go for it.
This one, maybe the one. This one, I think it.
Uh-huh.
The traffic background they have used. I don't know whether it's brown. It's making the thing not clear.
Interesting. Sorry.
Yeah.
What about now? I'm zooming there a little.
Okay, it's okay.
Mm,
You can continue.
okay. So, if we understand, I brought a question here that we can try. So this is the first question, and there's a follow-up question here. So, maybe we give ourselves like 5 minutes to see if we can try our hands on it. So maybe do this one. When you finish, you tell me, then I'll move to the next slide. So, can you try your hands on it? I beg, are we doing it? I beg, are we doing
Yes,
it?
sir. Yes, sir.
Okay.
Ravi,
Yeah, please, I'm here.
please, I don't know, but if you can go to the other page so that I'll take a screenshot, then you come back. But I'm done with this. So please, I'm done, so you can go back. Thank you.
Oh, okay. But I think we are all done with this one, right? So maybe I'll just keep the slide here for now.
Hey,
Yeah, how is it going? Are we done with the first question, the resultant amplitude? Or we are stuck?
Yeah, I'll end it, sir.
Yeah, okay. So you remember the formula we generated for the resultant amplitude? You can use that formula to solve it. And you can also go through the normal way if you be very confident by adding these two waves. Is that okay? Adding 5 sine into bracket our angular frequency time plus our pi over 2. Do the same thing, then you add the two of them together. And you take time for your trick to work very well. Is that okay? Then you find the resultant amplitude. So in other ways, they will also work. Then when you finish, we generated a formula for the angle, the phase, as tan theta equals, we had something like A, let me go back and check, A sine theta all over A cos theta. You can also use this one to do it. So this formula calculates the resultant amplitude. This formula calculates the phase, is that okay, of the resultant wave. And all these parameters has been given. So you can just be doing substitution. You punch your calculator and then you get an answer. I beg, is it clear? Yeah, Seth, are you done?
Yeah, please go over again.
I should go back, okay.
No, go over, go over, over.
I should go over. Okay. So I'm
Yeah.
saying you are given two waves and they are all traveling together. And under superposition, you want to find the resultant of them. In fact, we can find resultants in terms of amplitude. We can find resultants in terms of their phase. Is that okay? Now, we generated these two equations from this whole thing. Is that okay? And I'm saying that you can use this one straight away to do it, or use this straight away to do it. Or I prefer using the conventional way like this if you are very confident with it. Is that okay? This is more accurate. But still, you can use this one to do it. This is for finding the resultant amplitude. This is finding for the phase of the resultant wave. Is that okay? So here in the question, you have to look for your first amplitude, second amplitude, which is in the question. Is that okay? You have to look for your phases. That is the alpha 1 and the alpha 2. When you look at the question, this is your first amplitude, this is your second amplitude, this is your alpha 1, this is your alpha 2. So normal resubstitution, you get your pick A. Is that okay? Now, if you want to find the phase, is that okay? It's just as simple as tan theta of this whole term that we have here, right? Now, if we have something like this, the first amplitude is given, first amplitude is given, first phase is given, first phase is given, second amplitude is given, second amplitude is given, second phase is given, second phase is given. Is that okay? So normal restitution, then you are done. When you finish, you want to find angle, you find a tan inverse, and you get your angle. So let's hurry up. Fire, did you understand what I said? I beg.
Yes, sir. But sir,
Great.
have you shared the slide already? Because last week I said I asked you and said you are going to share it, but I've not seen it on the page.
I'll share it, don't worry.
But
Let's
please let me
finish with
let me.
today's.
I want to see. I want you to be on the equation, the other one.
The formula.
Yeah, the formula. The formula. Thank you, sir.
Sapphire, your hands is up. I didn't see it. Don't say something. Or you are done.
No, it's an old answer.
Oh, okay. Please, everyone should try doing it. It will help. So just try doing something and give me an answer so that we compare answers. Then I'll give the final one.
Ferrari, please, can you go to the question again? Okay, thank you.
Sir, please, the first one, I got 11.60.
The first one.
And the result and all.
You said the first one was
11.60.
11.60. Great. Okay. The second one.
I think 72.26.
Sir George, please be precise. The way you said you think. 11.60.
By 75, it is around there. So
Okay.
72 point, I think, yeah, 72 point some coins.
Okay. In degrees, I
And
guess.
then, yes, yes. Then the last one, because the first one is 11 points. So you get the 11.6
Mm-hmm.
sine WT plus the 1.2, because I'm only plotting the value.
Mm-hmm.
The 1.26. That's that's what I got. If we can go through it and also give the
Let's wait
test so
for
that we come.
the contribution.
Okay. Okay.
Thank you.
You're
Any
welcome.
different answer? Sir Michael, have you done something?
Yes, so the first one I got 10.68. The amplitude resultant
10.8.
68.
Okay.
So I want the second one and the third one. I'll put it like that.
Okay. So hurry up when you finish then. Yes, any different answer. I want a second throughout answer, then maybe we move on to the next thing.
Sir, please, as we wait for them, I want to ask a question. I'm
Yes,
seeing
please.
two formulas in the book. Say, if they are moving in the same direction, you add, right? So
Mm-hmm.
the one that is opposite direction, you subtract. That is,
Sincerely, we will not look at waves at opposite direction. Is that okay? We are always looking at it in the same direction. That is where we get to add or subtract and other things. But supposing waves are moving in opposite direction, it's a different thing altogether. Is that okay? Mhm. So interference, superpositions, everything we are looking at here, they are all moving in the same direction.
Thank you.
Mm. Yes, FIR.
So I got 12.0 for the first one.
10.0.
Yeah, for the amplitude.
Mm-hmm.
12.0. I'm still doing the
12.
second one.
Okay.
12.0.
12.0. Okay. So now I think I also did some solutions here. Maybe we can go through briefly. And I think I don't know the answer that I had. I got about 11.6. But anyways, let's go through briefly. So as I said earlier, for the first one, there are two ways going through it. Is that okay? I don't know the one that you'll be very confident with, but any of them that you think will do well for you, then you go through it that way. Is that okay? Now, if you remember, when I was explaining how we got the answer, we went through this procedure. We said that anytime we want to find the resultant, we add the first wave and the second wave. And of course, we can represent the resultant here by this whole term. That is the resultant amplitude, the sine of our angular frequency multiplying the time plus the phase. Simple as that. Is that okay? Now, in the rule of trig, anytime you have a sign AB, it means you have sign A cos B plus cos A sin B. This is a rule in trig. It's not my generated formula. Is that okay? Now, if we have this, of course, we can compare this to our final one or resubstitute this one into what we have here. So if I have sine omega, sine angular frequency multiplying the time plus pi 2, it means that it's the same as sine angular frequency time cos pi 2, another cos angular frequency time sine pi 2. Is that okay? And that is what I have here. So we are just following trick to open this term up. Is that okay? Of course, my 5 still comes here. Now, if I use calculator to punch for cos pi over 2, cos pi 2 is 90. Pi 2 actually is 90. So cos 90 is going to give me 0. Is that okay? Which is going to let this whole term here goes into 0. Now, if that happens, it means that I'll be left with only this term, right? Now, if I find sine 90 is going to give me only 1. And if that is the case, I'll be left with what? Cos angular frequency multiplying the time by the 5 that I have here. That is my amplitude. And I get my y in simple terms as I have here, generated as this. Is that okay? Again, I want to do for the y2. If I have 7 into brackets sine angular frequency multiplying the time cos pi over 3. In simple terms, I'll just, if I use the calculator to punch for the cos pi over 3, use calculator to punch for the sine pi over 3, in simple terms, I'm supposed to get 7 over 2, multiplying the sine angular frequency and the time plus 7 square root of 3 over 2 was what? My angular frequency time. In simple terms. Is that okay? Now, this thing that we have, we can generate our A and our B from it. Is that okay? That is our amplitude. So this is my first amplitude. This is my second amplitude. Because this time around, if we want to substitute out, of course, we can substitute this one out. Then, because we are just adding these two, is that okay? We want to add y1 and y2. And then from the resultant, if you add y1 and y2, you're supposed to get this whole term that we have below here. Is it okay? So you get this whole term here. There's a cos and a cos here. So the 5 will add this one. That is what we have here. Is that okay? So we add this whole term. It means that my first amplitude can be represented as the 7/2. My second amplitude can be represented as 5 plus 7 square of the 3/2. Is that okay? And what I have to do here now is to just remove the a and b and square root it. Find the square and square root it. And you just do this one as simple, you get your answer in simple terms. But if you're not confident with this and you want to go through the normal procedure, you should still get an answer. The normal procedure is going to give us, if we have formula as the square root a squared, that is the first amplitude, plus a squared that is the second amplitude, plus 2a1 a2 is the cos of what? Let me confirm the formula. Cos of alpha 1 minus alpha 2. Here, which one is going to be our alpha 1 and which one is going to be our alpha 2? And the class help me. Which one is going to be our alpha 1? Which one is going to be our alpha 2? We want to find the resultant amplitude using a different way.
So the alpha 1 will be 5. The alpha 2 is 7.
No, the A is rather 5, and the A1 is 5, A2 is 7. Look at this one. A1, A2. Alpha here represents the phase. One here represents the amplitude. Is that okay? And A2 here, of course, represents the amplitude for the second wave. Now, if we want to, of course, find the phase, that is alpha 1 inside here. Inside here is a phase. Inside here too is a phase. So, Sir Michael, can you come again for me? Hello. Am I online? Hello. Hello.
Yeah, we can hear you.
Ah, you can. So, Fire, if you can hear me, answer the question for me. Which one represents? You gave me an answer. Which one represents the A here? Which one represents the alpha here? This one. Let's go here. Which one represents the A1? Because I want 4 terms here. I want A1. Come again.
I think the alpha there will be pi/2.
Pi/2.
For y1. The y2 will be pi/3 for alpha 2.
Perfect. Perfect. Is that okay? Very, very simple.
Hello. Sir.
Yes, yes.
Hello. Yeah, I
Yes,
use
sir.
the formula straightforward. That is AR is equal to the square root of A squared plus A squared plus 2. That is it. So the first one I use 5. If you put it in, I put in 5 squared plus 7 squared plus 2 times 5 times 7 cos of when you do your deduction, your subtract, you get negative pi/6. So that's what I. So mine was for. That's why I was quite well. I didn't go to the step.
Okay. So let me write something here. We are trying to compare this equation with this A1 sine into bracket my angular frequency multiplying the time minus alpha 1. This is a general equation. And I'm asking the class, from this equation that we have here, what is going to be my A1? What is going to be my alpha 1? We're supposed to compare it with a second wave equation. Yes, say alpha, say fire. We're supposed to compare it with a second equation as A2. Is that okay? Sine again the same, because they are all traveling the same direction. We expect it to have the same angular frequency one with the other. Minus this time around, our phase here is going to be alpha 2. Is that okay? What I want from the class is what is going to be my A1, what is going to be my alpha 1, what is going to be my A2, what is going to be my alpha 2. We are comparing these two equations.
So
Yes,
the
the matter.
A1 is 5.
A1 is 5. Yeah. And what is going to be my A2?
So the A2 is 7.
2 is 7. Is that okay? Now, what is going to be my alpha 1?
It will be pi over 2.
Okay. I'll give you 4 over 2. Come again with that.
That negative pi over 2.
Now let's go to the alpha 2. What are we going to get there?
Alpha 2 will be negative pi on 3.
Negative 3. Perfect. Now, with these things that you just generated, what I need from you now is resubstitute what we just had in this formula for me and tell me the answer. Use the calculator to just punch. I've written the formula down here. Just resubstitute it. The A1, the A2, plus 2, that is all squared, plus A2, A1, A2. And now we bring in the alpha here as what? Alpha 1 minus what? Alpha 2. And please note
So
that
sir, that is where I got the problem. Why you have the alpha 1 and alpha 2? I make it. I saw it as A. I saw it as A. Okay,
so
thank you,
it's
sir.
good sometimes to
Thanks.
solve the question. So now we substitute these things inside here for me. Now you know that your alpha 1 here is negative pi on 2. Is that okay? Now you also know that your alpha 2 here, so you still bring our negative sign, then we bring in a bracket. Our alpha 2 is what? Negative pi on 3. So you can just do this one outside. Maybe when you finish, then you put it in our term here. Is that okay? You find the cost of it. So do this one and give me an answer. We are just calculating for the resultant. Is that okay? Yes, George.
Yeah, if you also do 2 pi over 3 minus pi over 2, you get it straightforward.
Yeah, of course.
You get it straightforward.
But we are just doing this so that in case there's a term of different signs and other things, no one confuses him or herself. Is that okay? Of course, when you do this negative, you get a plus. So it's the same as pi over 3 minus pi over 2. Yes, Michael, your hands is up.
Hey, that's an O hand, so I'm taking it.
Okay. So I'm waiting for you. Just substitute what we just did and put it in a calculator for me and give me an answer. Any answer for me?
Sir, I had 11.9998. Sir Ravi, Sir Ravi,
Yeah, hello, sir.
I had 11.999.
That's perfect. Any, as far as we are getting 11 point something, I think I'm good. Is that okay? Mhm. Because when you run it, from my answer, we are going to get about 12. So we run yours too, we are going to get 12, which is fine. Yes, sir, Francis.
So Rabbi,
Yes,
I
sir.
got it the same. Initially, before we did this, I got 11.99 and I rounded to 12.0. That's why I
Mm.
put it on my answer was 12.0.
Yeah, you gave your answer as 12.0. Oh, then you did
No,
well.
I got 11.990.
Yeah, perhaps.
Then I rounded to 12.0.
Okay, that's fine. Thank you. So let's go on. Any question from the first solution that we have gotten so far? Let's go on to the second problem. The second one, we want to find the initial phase angle of the resultant. Is that okay? And there's a formula for us to do that, which is also very straightforward. We can either go through this way as I've presented it here, or we go through the conventional way. And the conventional way, we already know the formula here. Is that okay? As and now, you know what A1 represents. You know what alpha 1 represents. You know what A2 represents. You know what alpha 2 represents. So just do substitutions of these ones and give me an answer. So you know that alpha 1 is negative pi on 2. You know that alpha 2 is negative pi on 3. You know that A1 is 5 and A2 I think is 7. Is that okay? So you substitute and give me an answer. When you put it here, the answer that you get is not going to be your angle. The answer that you get is going to be a tan theta of the answer. So if you want to get to the angle itself, you have to find the inverse of it. Is that okay? So let's do that and give me an answer back. Please, how is it going? Are we doing it?
Yes, please. You're on it.
Okay, sir.
Hello, Serabi.
Yeah, hello. Hello.
Please, I
Hello.
got negative 1.0. Yeah, hello. I
Oh,
got
there's a negative
negative 1.0.
negative 1.08.
08.
Okay. Any different answer so far?
I got 72 point. The B, right? The face angle. I got 72.2. This is running 72.3 degree.
Okay. So Solomon, did you find the inverse of it, the tan inverse of the answer that you had? Because when you finish in radian, you're supposed to be getting around 1.26. And you're supposed to be in degrees, you're supposed to get 72.45, as Sir just told us. So maybe let's do it this way. Let's take our time and go through so that our time here is running fast. Is that okay? Then maybe next week I'll ask you about it before I start the class. So when you're able to get the amplitude, you're able to get our phase. Is that okay? And the question is asking for the resultant equation. This is our resultant equation. Is that okay? The only thing left for us here is just a substitution. We have to come and replace the big R here by its resultant amplitude. Come and replace the phase here by its resultant what? Phase. And voila, we are done. Is that okay? So at the end, we're supposed to get a resultant equation as this by just a mere substitution. And this is a full question. So if you get something like this and able to go through, voila, is that okay? Any question before I move on? Sir Bismarck, I've not heard from you today. Sir Bismarck, are you on the line? Okay. So please, can I go on? You can give me a thumbs up if you guys are good. Then maybe I go on. Are we all good? Sapphire. Yes, Sapphire. Talk to me.
So we are good, you can continue.
Okay. Now, the next thing that we have to look at is one, that is unit 2. The first thing is interference. And as of now, we've gotten a small taste of how interference is supposed to work. Is that okay? So we'll be looking at interference. Of course, we will dive more into constructive and destructive interference. Then we look at Thomas Young. He did a very wonderful experiment to demonstrate interference. And we look at a very typical example application of interference, that is into thin films interference. Then under the principle of interference, sorry, there's one particular man who use interference in a basic principle. We call it interferometer. It has a very wide applications. Even in my lab, we have a setup. We have one man, Senyande, who worked on interference, and he used interferometer, and of course, he used it to check how strong a wood can be. Exactly. So when you go to the standard authority, they have a way of checking how the stress and the strain of a material is. Okay, so from Young's modulo, they use that one. Here it's not the Young's modulo. This one is Thomas Young. Exactly. And this time around, he used this one using interference to check the strength of the material and other things, which is a very nice application. So I'll be talking more about it later. Now, from what I told you earlier, we have something for the constructive and destructive. And now you should be able to explain what a constructive interference is and what a typical destructive interference is. Is that okay? Now, if we have interference, and we want interference to occur. There are two most important things that you have to look at. The first thing is coherency, and the second thing is monochromaticity. Is that okay? We are saying that our coherent. Is that okay? And when you say they are monochromatic, it means they have a single wavelength. So the white light that you are using, it's composed of a lot of wavelength that you know. Now we want a single one. So if it's red, we have a particular red that we want to take, a particular wavelength. Is that okay? We take only that one for this kind of interference condition to occur. And when you are saying coherent, it means if they are in constant phase, I have a phase like this, and another one is coming. If I want it to be a constant phase, it should also be the same as this one. Is that okay? Another one should also behave the same as this. So here I will say they are in constant phase. Is that okay? And a very typical ideal light source that can do this is a laser. Laser is a monochromatic, and it's also coherent. Is that okay? So we can actually use a laser to do this kind of an experiment. And during the practical session, if there's supposed to be a practical session, in fact, I'll demonstrate this one to you. And it's a very interesting thing. Is that okay? You actually observe interference with your own eye. So this is the man, Thomas Young. So we are talking about the 18s. He did very wonderful work. And after getting the coherent light source, getting our monochromatic light source, we need two things. We need a first slit and a second slit. And this is my first slit. This is my second slit. And if you remember, when you are doing rectilinear propagation of light, you punch a hole in the cardboard and you place it together in line. Is that okay? The same thing that we are doing here. But here, the hole that you've punched is very, very small. We're talking about a micro diameter. Is that okay? And we have another second screen or second slit that you've placed here. That one has two of these holes, one hole here and one hole here. Is that okay? But let's look at something here. What is going on here? You see, when light enters, you see how the apparel, when you see something like this, it means the apparel and they enter like this. This time around, look at how they are behaving. Which phenomena is going on here? Can someone help me here?
Diffraction.
Diffraction, perfect. Thank you. Is okay. So diffraction actually happens here, and it hits a second board here, which we have two holes. So the holes that we have here, I'll be calling it a slit. Is that okay? So we have two slits here, one here and another one here. Is that okay? And of course, because we have it here, another diffraction is going to happen. Another diffraction is going to happen. But interestingly, when this thing happened, Thomas Young placed a screen here. And he saw that he knew the light source that he was using. It was a red light source. Is that okay? He noticed that he will see a very bright light at one end, followed by a dark one, followed by a bright one, followed by a dark one, followed by a bright one, followed by a dark one. As and now, he didn't know what is going on. This is very interesting. Is that okay? So now let's look at something. He called the white one, the bright one that you are getting here, as the bright fringes, where he sees the light. And right after the bright, there's a dark spot that comes. That one, it's called the dark fringes. Is that okay? And followed it is about another bright one, another dark one, another bright one, another dark one. Is that okay? On the screen. So this is my viewing screen. Is that okay? These are my slits, first slit and the second slit. Second slit, we have two holes there. First slit, we have another hole here. Is that okay? And later on, I will explain. In fact, we need two slits before this experiment can work. But there's another experiment where only one slit can actually work. And you'll be looking at it in the fraction section. Is that okay? But for this particular, we need two of them. The first screen, which is composed of one slit, and the second screen, which is composed of two slits. And our very last screen as a viewing screen. Is that okay? So light enters, diffraction happens, the same light enters here, the same light enters here. Another diffraction happens. Is that okay? And we get this. So I'll be explaining why we are getting the bright fringes and what's the meaning of the bright fringes and why we are getting the dark fringes and what's the meaning of the dark fringes. Okay. So fast forward. These fringes here that we have here, the bright one is called the constructive interference. Is that okay? And the very dark one is what we call destructive interference. So constructive, destructive, constructive, destructive. Is okay. So where he was getting the very bright one, the light that he used, that is called the constructive. Where he is not getting any light at all, that is where we call the destructive. Now, this thing can actually also happen the same way, one way, the other, in different principles. When we have, say, two, let's say there's a stable water there, and we have, let's say, two taps on the water, and there's one experiment that we call the water channel vibration experiment or something, and here it's just like a finger touching the surface of the water, a stable surface water. But this time around, they've placed kind of a wood thing with a motor, which automatically touches the surface. And here they use two poles. Okay. So they were looking at if we do it the same time and different time, what is going to be observed. And in fact, you can actually also observe constructive and destructive interference here. But maybe I'll come back to this one later if there's a need. Now, let's go through the individual interference that was observed and how the constructive was actually observed and how the destructive was actually observed. Now, when you look at this is my second slit. The first screen has only two slits, only one slit. The second screen has two slits. So one exit. I know that a waveform light wave supposed to behave like a transverse. Is that okay? So I have my transverse traveling, But interestingly, if two of them are traveling and they are in phase, that is where I was getting the bright fringes or the constructive interference. And here you can observe that I have a crest here, I have a crest here, I have a trough here, I have a trough here. They're in phase, crest, trough, crest, trough, crest, trough, crest, crest. Then they meet here, and I get what? A bright fringes. And this didn't happen in only one spot. It happened at different spots of my viewing screen. Even at this point, it was behaving the same way. You see, the distance that this one is traveling is more than the distance that this one is traveling. But it's able to cover up for me to get a bright fringes. But in a situation like this, you can see that they are not in phase at all. When I start from here, you can see that we have a trough and we have a crest. We have a crest and we have a trough. We have a trough, we have a crest, we have a crest, we have a trough. A trough, a crest, they are not in phase. So they cancels out, which you know that anytime a phase is not in phase, a two wave is not in phase with the second wave, they cancels out. Especially if they are not in phase of about 180 degrees. Cancels out automatically. Exactly. And here we don't see any light at all. And that is where Young was actually observing the dark spots. Exactly. So now that is where we are getting the destructive interference. Now let's go to the mathematical principle behind this. Any questions so far before I move on? So you can give me a thumbs up if you want me to continue so that I know that we are all good. Okay. So now we have a constructive interference and we have the destructive interference. Let's go to the mathematical principle. Now I'll make this one a little big. I have a light source here and I have a second screen containing two slits. And in between the two slits, I have a distance D. Is that okay? And from my slit to my viewing screen, I have another distance. Here, I'll call the distance big L. Is that okay? Now, a very typical example where I have two waves that is traveling to meet at P. Now, I'm going to call here is the center line because that's the point between the two slits. I'm going to call this center line to where I'm getting my, say, constructive interference, that is the bright fringes, as Y. So another distance. And here, the Y is very important. Is that okay? Because we want to know at which position will I be getting a constructive interference or will I be getting a destructive interference? Is that okay? And the angle between my center line and where I'm getting the either the constructive or destructive is going to be my theta here. And it's the same theta that we want to also consider here. That is the distance traveled from one slit and the distance traveled from the second slit. Okay. So here, one waveform is traveling, that is my R1. Another waveform is traveling, that is my R2. Now let's consider only the R1 and R2. You are segmenting it out. Is that okay? To this. Is that okay? Now, if I want to find the distance between the R1 and the R2, that distance is going to be only at this end. Is that okay? So it means the distance that I have here is going to be equal to subtracting the R1 from the R2, which we have here. Now it's going to be equal to, now I'm relating the angle here. We know that anytime we have a sine is what? Opposite over what? Or adjacent? Someone should help me here.
Opposite over hypotenuse.
Opposite over hypotenuse. Very good. Is that okay? So if this is my angle, my opposite is going to be the difference of that I have here divided by the hypotenuse, which is going to be my D. Is that okay? Now, if I make only the D sine theta the subject, of course, I'm going to get R2 minus R1 because we know that is this equals the small difference of distance here. So this is the first equation that we are deriving. Is that okay? And here, this is the distance, the path distance. Is that okay? So this is the first equation. So now the path distance is equals to the D sine what? Theta. Should I go on? Okay. Now let's put this formula in mind. We are building on it. Now, if we want to observe a constructive interference and destructive interference, there's actually an order number that we have to observe. Is that okay? And from our constructive interference, or where we will be getting the bright fringes, the distance, the path distance that we have to consider is D sine of theta. And here we are talking about adding an order number of an integral of, say, M to find a wavelength. Is that okay? So if you know the wavelength and we have the distance and we have the angle, it's easy for us to find the path difference, or likely to also find the wavelength. Is that okay? So this is for constructive interference. So what we derived equals an order number multiplying the wavelength. Is that okay? But the destructive interference is a little bit different. This time around, the order number plus half. So the same thing, but this time around, the order number plus half. Is that okay? And in fact, this formula is very important because if we have this formula and we have a light source and we don't know the wavelength, supposing we don't know whether it's 600 or 650 nanometers, we don't know. We can actually use this experiment to determine the wavelength by just experimenting and finding for our D, finding for our angle. And if we don't even have the path difference, this one we don't mind. Even getting this one and this term, we can find the wavelength. Is okay, as straight as it is. And there are a lot of experiments that we do, even with some of the students here, to find the wavelength of sodium light. And when they do that, they just find the angle. But here we use a grating. Is that okay? We have a example called a diffraction grating. They use it to find the different angles, and the grating has a particular distances of groove among them that is used to find the D. And at the end, we can find the what? The lambda. Is that okay? So we can use it to determine the wavelength of some light sources. So this is for dark, this is for bright. Is that okay? Before I move on, any questions? There's an hands up. Yes, Kojo Anefi.
Hello, sir. Please, good morning.
Good morning, sir.
Is there any reason? I mean, I want to know the significance of the half that has been introduced into the distractive interference. I mean, why half?
In fact, when it comes to some constants and some integers that are being added to something like this, is to differentiate the first one and the second one. Is that okay? So the half here is signifying the different positions apart from the normal bright fringes. Because if we don't have the half there, of course, we are going to get our normal bright fringes. Is that okay? So when we have something like this there, it means it's per some experiment that was done. That is why it brings some integers or some constant in the formula. I don't know if you understand what I'm trying to say. So we perform this from where it has been derived in a perspective. Is that okay? It is performed, it's okay. So anytime that we have a bright and a distant, we have or an integer added before we can get this. Is that okay? So it's just differentiating the bright fringes and the dark fringes in general formulas. I don't know if I've answered your question.
All right, sir. All right, thank you.
You're welcome. So please let's keep in mind this formula. We'll be building on it as we go on. Apart from Serena, if you any other question, so that we address this before we move on.
Sorry, another question. The part where we were going through, like between the first the first screen and then the second screen, where we were showing the description of the Young's apparatus. Please, between the first barrier or the first screen and the second screen is how do I call it? Does distance or the separation matter?
This is a very nice question. In fact, it do matters. But in terms of observing the bright and the dark fringes, it's not really considered in the question. Is that okay? Here, parameters that were actually considered is the distance between the two slits of the second screen. Is that okay? And of course, the distance between the slit and the viewing screen itself. But if we are doing it experimentally, you will see that if there is a distance, there's a difference in intensity when it comes to how bright or how still on the bright fringes, but you see how very bright it will be or very how dim it will be. The distance do matters. Is that okay? But if there's a need for us to look at it, maybe it will surface and we'll also look at it. But now we are not considering the distance between them in terms of the formulas we are looking at now. Is that okay?
All right.
Thanks for bringing it up.
All right, sir.
Okay, so we are done looking for the two formulas. Is that okay? Now we can find the wavelength, we can find the angle, we can find the D, the distance between the two slits. Is that okay? We can find all of these ones. Now, let's consider something. I want us to bring the L on board. And the L that we are talking about is the distance between the slit to the viewing screen. The viewing screen is where we are observing the bright fringes and the dark fringes. And this is not any microscopic thing. Like you will see it, the light is there and you see it on the screen. I'm doing the class in the house, so I can't show you anything. I could have maybe done something small for you to observe it. You just see it on the screen very nicely. Bright one, dark, bright one, dark, bright one, dark. Now the thing is, whatever being the case, of course, we expect that the distance between the slit and the viewing screen should be way more than the distance between the two slits. Because the distance here can actually be in millimeters, but the distance here can be in a centimeter or even a meter. Is that okay? So whatever be the case, our assumption here is L is far, far, far greater than the D. In the same way, we expect that the distance here should be also far, far, far greater than the lambda. That's the wavelength of the light source. The wavelength of the light source, in visible, we are talking about nanometers. The distance here, we are talking about millimeter. So it means D is way, way, way greater than the lambda. And if we do that assumption, we can, of course, consider something here, still under trick. If I want to find a tan, but this time around, I'm considering the brown shaded aspect. Is that okay? So I have my theta here, I have my length here, as y, I have my big L here. Is that okay? Which is it? Am I going to use tan or sine or cos? Because I want to relate the big L, the y, and the angle here. So I want to make use of the opposite and adjacent. No hypotenuse here. Which of them will help?
I think this one they use that, right?
So unless we use tan,
Tan.
exactly. And tan is always opposite over what?
Yeah.
Adjacent. Is that okay? So the opposite here is going to be my y, and the adjacent is going to be my L. Is that okay? So if I make L the subject, I'm supposed to get y equals big L tan theta. That is approximately here. We are saying that if the angle here is super, super small, it should be approximately our L sine of theta. So now we are relating our y, ignoring the tan, and relating it with L sine theta. Now with this thing that we have, in the formula that we generated already, the path difference we said is d sine theta equals m alpha. M here is our order number. And here again, we have d sine theta equals m plus 1/2 lambda. Now, when you look at this, we can actually resubstitute this in here, because we know that if we want to make sine theta the subject, it's going to be what? Y over L. I want to ignore the sine theta here and bring y over L in there. Is okay? Because I want to be able to determine the point on the screen where I'll be getting my bright fringes. So which point should I move before I get a bright fringe? Which point should I move before I get a bright fringe? Exactly. So if we are able to do that, that will be very easy for us. I want to write pen. So if that is the case, I'm just going to ignore this. And here, my sine theta is what? Y on L. And if I do that, this first term that I have here is just going to be represented as d y on L equals my order number, that is m, and my wavelength. That is all. Now I'm interested in only the y, so I'll make y the subject here, so that I'll get what? Lambda L. So this L is going up here. Then I'll get all over, multiply the order number, all over what? D. Is that okay? And that is what we have here. The same thing can also be repeated in this for the destructive. And when you do that, we are going to get the y as this end. So it means that if I know the wavelength of light source that I'm using, I'm very, very particular, and I know the length of the distance between here and here. And of course, I know the distance between the two slits. It means that I can actually determine the distance that I have to be getting my dark spot. Is that okay? And the distance that I have to be getting my bright spot. And maybe I've not mentioned it. Let me tell you this. The order number here is very important. If we are the center line, this point here, the order number is 0. We move the first spot that we see, say the bright fringes. This is going to be order 1. The next spot we see for the bright is going to be order 2. The next spot that we see is going to be order 3. going on as such. Is that okay? That is what the other one is doing. At the opposite end, the same thing reflects. Is that okay? So still we are going to get our 1. So you know the distance between the 0 and 1 here is the same distance from the 0 and the 1 here. We're still going to get our 2 here. Let me zoom in. We're still going to get our 3 here. Is that okay? So you see I have 0 here, 1, 2, 3 going. If I'm able to observe 20 constructive interference, all the 20 points that I'm having here represent others. The same thing happening on the left will happen on the right, or in this term, as we are viewing it, happening down will also happen up. When we are using a spectrometer to observe this in the lab, we observe it left and right. But here that we are observing, we are just going to observe it as any UCC center student here, which people has come to UCC for an experiment before? Any students here so far? No one has been to UCC to perform any experiment before. Okay. Because I think they've done this, so I wanted to ask them a question. They've observed something on a telescope before. So this thing that we have represents the order number. Is that okay? So let's not be confused about the order number that I'm talking about here. Is that okay? Any questions so far before I move on?
Hello, sir.
Yes, I'm listening, sir.
Hello, sir.
Yes, sir.
If you have so many, as you stated, you have 3 here, 3 here. Then what will be the other number, or it will be the specific bright fringe that you are considering that you put the number?
Very good. So here, if you want to find for the bright fringes of Y, and I want to find which distance will I get order 3. So I want to know the distance from the 0 to the 3. That is what the Y here is calculating for us. Is that okay? So here I have to put in an order number 3 here, putting the distance between the S1 and the S2, the 2 slits, putting my wavelength, putting the distance between the slit and of course the screen. So Michael, do you understand?
Yes, please. Thank you. I understand it.
So if we are here is represented as positive and negative. So if we are talking about something like this, the top one is going to be presented as positive, the down one is going to be presented as negative. Is that okay? So the other number is talking about the individual point that you will be getting a bright fringes, which is very important. And you know, there's a plus half here. So it means we can also look for the spot that will be getting a dark fringes. And it's always between the bright fringes. You see 0 and 1. In between 0 and 1, there's a dark fringes there. In between 1 and 2, there's a dark fringes here. In between 2 and 3, there's a dark fringes there. Exactly. And we can actually also determine that distance Y that we can use to do that. Exactly. So from this formula, we can know the exact point, centimeters or millimeter, or even any meter, of course, distance, that we can find our bright fringes and we can find our dark fringes.
Hello,
Okay,
sir.
sir. So,
Yeah.
so with the dark fringes, the other number, if it is between 0 and 1, that means are we going to input 0.5 for the M?
No. So the half that is there covers up that issue.
Okay, sir. So that will
That
be
is
1.
why, very good. So if
Okay.
I want to find the dark fringes between, let's say, around this end, and my order is 1, I'll put 1 here, and there's a half there that will cover up the exact distance that I should be getting. So you don't have to do any. Just using the formula straight away can give you the distance that you get. Yes, Sir Eric, your hand is up, or you want to say something? Do you want to say something?
Yes, please. I want to ask a question. With the
Please
other
do.
number, I've seen that you've indicated either positive or negative. Well understood. Assuming you are taking another number of
maybe -1, are you supposed to indicate the negative in your formula, or you just write one?
No, you have to indicate it.
Okay, okay.
I'll
That's what
actually
I
give
just
a
want to know.
formula. Yeah, I'll actually give a question for us to. I don't know if I have a question. Yeah, there's a question here. So that we use it to experiment on this. Is that okay? Then there are conditions to it, which I will state if there's a need. Is that okay? But as far as there's a positive and negative, and the question states it, you have to factor in that. Is that okay?
Okay, thank you.
And this one is simple because if we get another number to be say negative, and at the end of our calculation, we are getting a negative value, it makes sense to us that if here is representing positive, of course, I'm going to get a distance of negative around this point. Is that okay? So it's just telling me the positions that I'll be getting my distance, my bright or dark fringes, whether it's going to be at the top or it's going to be at the down. So Eric, are you okay?
Yes, please. I'm okay. Thank you.
Perfect. Now let's try this question. When I bring questions, I think it takes our time. So I don't know whether there's really a need for questions. If I don't bring it to, I don't know whether you understand what we are doing.
Oh, sir, it's very necessary. Let's do it.
So please, only
Hello,
5 minutes. Yes, Sir George.
hello, I believe by this time we are entitled to about 5 minutes break. So I don't know if my colleagues will agree. So that we use that 5 or 10 minutes break to solve this and come back. If it is fine
Okay.
with them.
The way we wasted time before, I didn't want us to go on break, but it's fine. If we all agree we want a break, I will leave the question on the screen like this. Then we go for a break. Then as you are on break, maybe you use that time to solve it. So if it's 10 minutes, we are coming back. By 10 minutes, I know that we are all done. Then we go through together. Agreed?
Yes, sir.
Agree.
Yes, sir.
Yes, sir.
Mm.
Yes, sir.
Exactly at it's 9, almost 9:20. Exactly 9:30. Please, I'll be starting. Let's not go to the group to say, please, we are starting. Or let's just join at 9:30 and start this up. I beg you. Okay. So 10 minutes break. Hello, are we all back?
Yes, sir.
Okay. So, Sanefi, have you gotten an answer for me?
I got the the first part, the wavelength. I got it to be 563 nanometers.
5. Perfect.
Nanometers.
Then the second.
And then the second, I got 2.25. 2.25 times 10 to the power negative 2 meters.
2.25
times 10 to the power negative 2. Yes, 2.25 times 10 to the power negative 2 meters.
Negative 2 meters. Okay. 2 centimeter. Okay. That is fine. Any different answer apart from say Anefi's own? Yes, Eric, did you try?
Yes, please. I tried. I had the same
thing.
thing.
Perfect.
Yeah.
So
Yes,
I don't know who, if say Anefi will take us through briefly, very, very brief, before I go
on. Okay. So the screen distance in the question, the L is giving us 1.20 meters. And then the slit separation is giving us D, which is 0.03 millimeters. But then I changed it to meters, which was 3.0 times 10 to the power negative 5.
Okay.
So the M equals 2 tells that it's a second order bright fringe. And so I used the Y2 was 4.5 centimeters, which was 0.045 meters. Then we have our double slit bright fringe formula as YM or Y subscript M equals M wavelength L on D. I made Y the subject straight ahead. So Y equals MYL. Sorry, M wavelength L on D. So I solved for wavelength using M equals 2, and I have my wavelength equals YMD on ML, which is, we just plug in the values. The YM is 0.045, then the D was 3.0 times 10 to the power negative 5, M is 2, and L is 1.2. So that gave me 5.625 times 10 to the power negative 7 meters. And then equivalent to 563 nanometers. I don't know if that's okay, and I can go ahead with the second one.
Yes, that's perfect. So go ahead with the second one. Maybe the second one, hold on. So Eric should help us with the second one. Thank you. Hello, Sir Eric. Are you online? Okay. Sorry, Stanley, if you kindly go on for me. Sir Eric is not responding.
Okay, so here they are asking for the distance between adjacent bright fringes, or the fringe spacing. And that is changing Y will be equal to the wavelength times L on D. And already we have our values of wavelength, which is 5.625 times 10 to the power negative 7. We have our L to be 1.2, and we have the D to be 3.0 times 10 to the power negative 5. So once we plug in the values, then you have 5.625 times 10 to the power negative 7 times 1.2 on 3.0 times 10 to the power negative 5, which will give us 2.25 times 10 to the power negative 2 meters. And it is also equivalent to 2.25 centimeters. But I think the standard unit is, so I left it in meters.
Okay. That is fine. So, yes, thank you very much. That's good. So, this question is a little straight away. So, the struggle with it will not be that much. And, the first one that we are asked, we want to find the wavelength. So there's an experiment. What we did is take note of some parameters, like the order that we observed, the 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 length between the slit and the screen, the distance between the two slits, and of course, we want to the positioning that we had the bright fringes with respect to the center line. That one too is given. So we are given all these parameters. So we just do a normal substitution, and we get 563 straight away. Is that okay? Now, if you want to find the adjacent fringes, we are just interested in right beside it, the next fringes that you'll be getting. Is that okay? And right beside it, we're expecting something like a destructive interference, or another bright fringes, we're expecting a bright or constructive interference. Is that okay? In fact, if we add one or subtract one, we should be getting a likely answer. Is that okay? Because the adjacent, it wasn't speaking as whether the adjacent to the left, whether the adjacent to the right. So what we just need is we want to increase the order number. Is that okay? So we just increase the number by one. It will let us get the adjacent bright fringes. And in fact, you can actually solve these ones individually. And when you finish, you subtract. So this one is going to represent the very first one, and the next one is going to be represented as this. In simple terms, which you can do, but if you don't take care, you may deviate, is just dividing the distance by 2. Is that okay? You see, the distance that was given to us was actually 4 point, where is it? Yes, it's from the center line. It's 1.2 centimeters. When you actually divide this one by 2, straight away, you should be getting 2.2 centimeters. It's 2.25 centimeters, which is very, very right. Is that okay? But if you don't take care, you may deviate unless you understand the question very well. Is that okay? Is in simple terms divided by 2, because this is the order of 2. We want to look for the order of 1 or the order of 3. Is okay. So if you want to find the order of 1, and the distance between the 0, that is the center line, to 2 is 4.5, it means we want the middle one. So it means when I divide this one by 2, I can easily get my adjacent fringes. Okay. So any question before we move on?
Hello, sir.
Yes, sir, nephew.
I was asking, still on the half. I wanted to ask if another way of looking at it could be that the dark fringes occur maybe halfway or midway between the bright fringes, and that is why the multiples of half are kind of factored into the formula for the dark fringes.
Of course. You see, the order of these ones is 1, 2, 3, negative 1, 2, 3. And in between each of them is where we get the dark fringes.
Dark fringes, okay.
Yeah, okay. So it means if you are interested in the dark, and even we take the distance between the two of them, half of it is going to give us the dark. Is that okay? But the perspective that I was coming from was the fact that the experiment is actually done to derive some constants and some parameters attached. Is that okay? So this is not into a general perspective that, because it's this, that's why we are doing this. But it's because of a sequential experiment that has been done to verify a constant. And it's not only about this parameter. It's any general constant that you can think of. The Planck's constant, the Coulomb's constant, any constant you can think about. Is that okay? And that is how it's done. So the sequential experiment generates the constant and parameters around. Yes, Sanef, are you okay?
Yes, I'm okay. I was only coming from that perspective because you see, from the very beginning, you said that with the constructive interference, a crest must meet a crest and a trough must meet a trough. But then when we come to the other one, which is going to lead to the dark fringe, you realize that a crest must rather meet a trough. And for that to happen, it means that troughs, let me say, one wavelength has to be shifted halfway so that a trough can exactly meet a crest, and then that order. Because once they are aligned a crest and a crest will meet, a trough and a trough will meet. But then
That's
for
fine.
the dark fringe to be happening, it means that we need to shift one wavelength halfway so that the trough will meet a crest. And that's the perspective that I was coming from. That's what I wanted to be sure.
Yeah. So, anyways, we when we are saying this, we don't say we shift it. They are out of phase of 180 degrees. That is the perfect way to say it. Just to add up, is that okay? So you say they are out of phase of 180 degrees.
Yes.
Okay.
All right.
Yes. Nana Kwame.
Sorry.
Mm-hmm.
Yeah, you just gave the shortest, way to determine the distance between adjacent fringes. That's by dividing the distance between the slits and the screen given as 4.50, divided it by the order number, which is 2.
No, it's not divided by the order number. It's divided by just 2 because we are having it.
Oh, okay, all right. So I thought it's by dividing it by the order number. And so whatever order number that is given to you, you divide by the distance, you will get the distance for the adjacent circle. So I was thinking you use the order number given. Okay.
No, it's good you
so irrespective of the order number, you have to divide by 2.
It's good you've got this enough. You said, you see, when I was about to answer this shortcut, I said, unless you understand the question very well, other than that, you may deviate. In the question, we are giving the distance from the center line. Here is the center line, 0. To an order number stated in the question as 2. Now we are interested in the adjacent fringes. It is going to be 3 or 1. So in simple terms, we just want to look for, say, 1. And supposing 0 to 2 here, our distance y is 5. If I want to find the distance of 1, I'll just divide by 2 because it's half of it. Is that okay? And now the distance that was given the question is 4.4. 4.50. Very good. Y, that is y. That is from the 0 to the order number of 2. So if I want to find a 1, I just divide by 2. But if the question changes and you're starting from 0 to 3, you can divide by 2 unless you understand the question to use a short form. I beg. Is that okay? So let's be safe. Let's know how to play around it. If you think you understand the question, you use a shortcut. That is fine. I don't have, because the shortcut will help in answering some of these objective questions. Other than that,
sure.
let's do it normal way. I beg you.
All right, sir. Thank you.
You're welcome. I have another set of questions here, but maybe can we just do a screenshot? Maybe when I teach more in 10 minutes, maybe we can go back and do this one. In fact, this question is almost the same as the one that we just solved. It's just some small parameters that has been changed. Parameters like the distance between the 2 slits, the separation, of course, here, and we have the separation between the slit and the screen, and the distance between the 2 slits, and the fringes. The fringes is even the same. And I think the distance from where we had our fringes is okay. So something like this, we can easily do it. So maybe we can skip this question. But let's look at a question like the second and the third one. I think there's an hands up. Service might ask. Yes, come on board.
Good morning.
Yeah, I called you earlier, but I think you didn't.
Yes, so please, that's why. Yeah, I want to speak to that. If I have to attend to some emergency, seriously. So I'm back now for the second session. So sorry about that.
That's fine.
Yeah, thank you. Yeah, thank you.
Okay, but I think this class is being recorded, so maybe when we are done, then
yes, I wanted to say that if the recorded version is there, then we can make it available so that
so code will
can go through. Okay, all right. Thank you. Thank you, sir.
You're welcome. So I think we can go through these questions later. Is that okay? The first one is almost the same as we solved earlier. The second one is you should be very, very familiar because we are just finding the wavelengths. Is that okay? But In finding the wavelength, there are two ways that I've shown you now. There's one way of using this formula, and you have to know that there's another way of using this formula. If you are given the angle and you know the distance, you can easily find the wavelength too. Is that okay? So let's not put all hopes here. Let's just also look at this end. That's why I started proving this formula, starting from this perspective. Is that okay? Okay. So now let's look at something here. If it's a different thing that we are going to do here, but let's just look at it. Still in terms of phase changes. And now you understand a phase change. Is that okay? So when you say something is in phase, you understand. When something is out of phase, you understand. When something is in a phase change of 180, you should understand. And maybe just for reminding you purposes. So if we have a phase like this, and we have another phase like this, we say they are all in phase. But when I have a phase that is behaving like this, I'll say they are out of phase. And out of phases are in different angles, depending on how the shift is. Out of phase, like something like this and this, we say they are 180 degrees out of phase. Is that okay? They are 180 degrees out of phase. And in this way, the crest is here, the trough is here. The trough is here, the crest is here. Agreed. Now let's look at something. Anytime light hits on a surface, depending on how the surface is, whether hard or whether rigid, or let's say whether raw or whether denser, it may change the phases of this light source. Is that okay? And that is what we are interested in. Now, you can imagine this one as you having a rope tied on a very rigid support end or wall, and you try to move the rope up and down. Is when you move it up and down, it causes this wave band that it can travel to that end. In fact, when it reaches there and it's coming back, the reflection will not be the same as you gave it. It will turn to the other end. Is that okay? So you see that here, the incident is going, the one that you are standing here, and if you move it up and down, you get this up here, it hits the wall. Instead of it to come out this way, no, it doesn't behave that way. It comes out in a different way. Is that okay? So here we say that it has changed the phase in 180. Is that okay? So where we have the crest, now we have the trough. In a situation where it's not a rigid support end like a wall, and it's a freely supported end. You see, the wall, it has a ring and is being held by a metal or something. In a situation like this, if I move it up and down, the incident hits the wall. When it's coming back, because this one can move, it hits, it moves up and down, I still get the same one that is coming back as reflected. Is that okay? So in the free end, or say a lighter medium, we have no phase change. Is that okay? What we give it to it is what we still receive. But in a fixed end or a denser medium, you will see that what you give to it will be changed in phase of 180 and it will be given to you back. The same scenario happens in here. Look at the picture I'm showing here. I have a rarer medium or a less dense medium and a more dense medium like a glass. Is that okay? You know glass has a more refractive index than air and it's more denser than air. So it means that when I have this kind of a wave, it hits the surface and the phase will change automatically. Is that okay? Because we are saying that if the surface is hard enough, it will change the phase. But if the surface is soft enough or less dense, it will bring the same phase to me. So you can observe that the first one that it changed the phase, you see that here is my crest. Now here is my trough. Here is my crest. Here is my trough. Here is my crest. Here is my trough. Sorry about the drawing. Here is my crest. Here is my trough. Here is my crest. Here is my trough. It has changed the phase completely up to 180, where we sent the incident and we're having a crest. Now, when it's coming back, we're having a trough. Interestingly. Now, in a situation where we are from a denser medium and entering or hitting on the surface of a less dense medium, this time around, no phase change is going to happen. Is that okay? So now in a glass, and we are hitting the air, supposing you are inside the glass and you are trying to hit the air that is outside. Is that okay? So it hits the surface. Interestingly, if there's any source of reflection that is going to come, this time around, it's going to what? Be in the same phase. So it hits, and you can see that the crest is here, we still have our crest here. The trough is here, we still have our trough here. The crest is here, we still have our crest here. Is that okay? And this is very, very important thing that we observe under reflection. Now, the whole principle is about their refractive indices, how less dense they are or how more dense they are. Is that okay? And if we have a refractive index that is, of course, less than the one that is going to hit them, of course, we expect that it will change the phase for us. And now, if we have a refractive index that is more dense and it's going to hit a surface that is less dense than like air, it means that we should expect a same phase without no phase change. Exactly. Very, very simple. Now, someone may even ask why this one matters, which we'll be looking at very, very soon. And one thing that we have to also look at, there's one experiment that actually depicts what we just explained. And we call this one Lloyd's, I think I wrote it somewhere. Is it Lloyd's experiment? Lloyd's mirror. Is that okay? And what he did is, if I have a light source here, and I have a viewing screen here, and I bring a mirror here, the light has its own wave that is traveling through. And because there's an extra distance that a wave is traveling through this end, it reflects, go back this way, it changes the phase of it. Is that okay? Before hitting this end. So at the end of the day, I have a light here. I'm expecting the light to say shine on the screen. But this time around, I don't see anything on the screen at all. Is that okay? Because of the phases changes that is happening there. Is that okay? So now I'm going to observe something we call what we just did, dark fringes. There's an extra distance that has been added. And from Young's modulo, Thomas Young that we just did, we observe that when it comes to distance, it's very, very important. Is that okay? The path difference influence constructive and destructive interference a lot. Now, this thing can actually be observed a lot. And when we started even talking about interference, I mentioned it. I mentioned the fact that we see kids play with soap water, and sometimes we used to use a broom, then we tie it at one end, then dip inside a soap water, blow air in it, and we get this nice bubble. This thing that you see there is because of interference. Very nice color pattern. And they all depends on how the phase changes happens. Is that okay? And I'll be explaining how these things happen one way or the other as we go on. And because we have a refractive index here, and because one is hitting the surface, another one, of course, enters because of refraction. And the same one is going to exit out. Now, from what we know right now, if it hits the surface here, it goes here, it means there's a phase change because we are from a less dense medium to a more dense medium. So here, there's going to be a phase change here. But now when it enters and it's hitting this surface here, because it's from a denser medium to a less dense medium, the phase doesn't change. Is that okay? So you can see that I have a crest here, I have a crest here, I have a trough here, I have a trough here. Is that okay? And it exits out. So now here, phase is changed, here, phase is not changed. Is that okay? And these variations that we get gives us the bright light there, which, of course, I'll talk again about it later. Now, let's look at something. We want to derive a formula here under thin frames. Now, you know this formula already. Is that okay? you know that there's a formula where refractive index relates the wavelength of a vacuum over the wavelength, of course, of the medium. Is that okay? As this. And if you remember, this formula dates back when we have something like refractive index to be equal to C on V. Is that okay? So C on V. And we know that anytime we have C on V like this, the C represent the speed of light, and V represent the speed of light in the medium. So speed of light in the medium, speed of light in a vacuum, which we can of course represent this one again by F lambda. Is that okay? And again, F lambda, because that is velocity is related to F lambda. Is that okay? Now, if we have something like this, the frequency that light travels in a medium doesn't change no matter what. So it means our F here can cancel this F here. And we'll be left with these two lambdas. Now, this lambda here represents the speed of light in a vacuum. And this lambda here represents the speed of light in a particular medium. Is that okay? And that is why we have this. So we just made the speed of light in a medium as the subject, and we have the wavelength. Lambda is wavelength. Wavelength of a medium equals the wavelength of our. Am I going too fast, or we are following?
We are following.
We are following.
Perfect. Now, if we have this, we are still talking about phase changes. And now the phase changes here, we are bringing thin films into place. And the reason why we are calling it thin film is the reason why we have something like a bubble. And you know, the bubble itself, the soapy water creates a layer, which is very, very thin. And there's light coming here to hit on it. Is that okay? So there are two surfaces here. There's a surface that is of air, and there's another surface that's composed of the bubble itself, like the N2 that we have here. Is that okay? But this one is very, very thin. That's why we call it thin films. Is that okay? And it's the same way when you see when it drizzles a little and oil is on the surface of some coat. In some of the coaters, you see, they don't do it well, so it leaks. You get some small oil leaks, and you see a very nice color or color pattern on the street, like on the coater. Exactly. And that one too is because of thin films, because of the nice patterns. So now let's go on if we understand what is going on. Now, if we have this, there are two things that we also have to consider. We have to consider the distance that it travels in the thin film. Is that okay? And now our distance is going to be the t. Is that okay? If we want to relate the wavelength to, we can also relate the wavelength as what? The wavelength divided by 2. And the distance that ray2 actually traveled is 2 times extra. Is that okay? So it's going to be 2 t, because it starts from here 1, then it goes out 2. Is that okay? So you're going to get 2 t. Now, because we are of course talking about phase changes, the first phase is this. Is that okay? The second phase is this. Is that okay? This phase changes, the variation that is in is a half cycle. And if you remember, when we were defining wavelength, we said wavelength is relatively at a full cycle. Is that okay? So if I have something like this, we said wavelength is from crest to crest or trough to trough. And I elaborated on the fact that even from crest to crest too, we can say wavelength too is also from what? One point here to another point here, which is a full cycle. Is that okay? That represents a wavelength, that is a lambda. But the difference in phases between the two of them that we are talking about is not up to a full cycle, it's half a cycle. Is that okay? That is 180. It's not 360, it's 180. Because it's 180, our lambda here is going to be lambda divided by what? 2. That is the half of the wavelength. So that is why we have this. Is okay? So now the phase change is making a difference. The path difference is also making a difference. We are just going to combine these two. And at the end of the day, combining the two, we're supposed to get 2 pi sorry, 2t, that is the distance that is traveled, equals our lambda. Is that okay? Divided by 2. And here we have to consider a particular order, that is our m. So this is the general term. But because we have our n to be equals to the wavelength in a vacuum divided by the wavelength in a medium, and we are just interested in the wavelength in a medium, we can, of course, make this a subject, and we get the lambda over n, which we can resubstitute it in here. Is that okay? And at the end of the day, we're supposed to get a formula like this. And the half there is just representing the order in relation with the what? With the m. Is that okay? So now, for a constructive interference, in this same thin film, we can, of course, calculate the wavelength of the light. We can calculate the refractive index of that thin film. We can, of course, calculate the distance that it's used to travel. And this thing that we are talking about here, the application, again, is very wide. When you go to the oil industry, they can use, and there's a spillage of something in, say, where they are doing their mining, they can use it to know the level of spillage on the surface of water. So you see, oil on even water gives this nice reflection. It's very, very thin. It's very difficult for you to also measure that thickness. But if you're able to measure the distance it's traveled, we are able to find the refractive index. We can know the material that is causing that. We know the refractive index. We can know the type of thickness that is happening there. We know the wavelength. We can also use it to determine the material. Is that okay? So this one too has a very wide application. Now, in terms of destructive interference, this time around, we have the order standing alone like m. Is that okay? So we have our m multiplying the lambda equals 2n, which is our refractive index, multiplied by t. Is that okay? That is our time. Please, any questions so far? Give me a thumbs up if you are good so that I continue. Okay. Now, I have another question. So maybe let's do only the, which one should we do? Which one should we do? Which one should we do? I want one that we will think plenty. Okay, you better still, let's go on to this one. Let's do the number 4. Only 2 minutes. So which point will produce constructive interference and which will produce destructive interference? Consider the individual points, the A, the B, C, D, up to I. Only 2 minutes. Please, are we doing it?
Yes, please.
Sir, I'm done.
Okay. Yes, so give me an answer. So let's go
So
to the which one is the constructive?
the construct, I can do it in order. J will give constructive, H will
Mm-hmm.
give destructive,
No, I want
I
only
will give
constructive. Only constructive.
transmission. Okay, J,
Mm-hmm.
and then J,
J.
and then
I don't see J
yes,
here.
there is J there.
Yes,
Okay,
J.
there's no
Okay.
J.
Mm-hmm.
Okay, then let me use the diagram. Using the
Okay.
diagram, you say that so A will give constructive, B will be
Mm-hmm.
destructive. Okay, you say you want only constructive. So please let me do
Yeah.
it. Okay, so A will be constructive. Uh, D will also be constructive,
Mm-hmm.
and then G will be constructive, and
Mm-hmm.
then H will also be constructive. H,
Okay.
H, and the destructive will be B,
Hold on with the
C.
destructive. I want a different answer. Hold on. Sir George, hold on, I beg. I want a different answer for the constructive and destructive. Is that okay? So let's hold on for a bit.
Like so when I say they use it to compare somebody's own, or
Okay, but so far it means what you have, the rest is destructive, right?
yes.
Mm-hmm. So that's fine. I will just wait for this to finish so that we compare answers.
Thank you.
Is that okay? Thank you very much.
Thank you.
Please, any different answer?
Please have the same answer.
Okay. Apart from Sir George, Sir Michael, yes, Sir Bismarck, come on board.
Yeah, so observing the waveform, I've noticed that the waves are out of phase by 90 degrees, lower than the. We are not going to experience the full interference that we know, but partial interference. So a waveform we produce actually affects the amplitude in some way too. That's my general observation about the waveform. Thank you, sir.
Okay. Sir Bismarck, thank you for your observation. As a matter of fact, what you are saying is very true. So you can imagine, let's say this one has an amplitude of say -4. This one amplitude. Okay, let's count every box as one. So we have 1, 2, 3, and 4. 4 is here. If we are supposed to count the amplitude of this, here the amplitude is 2. It means when we add this 2 to cause a destructive interference, it's not going to be total 0. Is that okay? But as far as we have a crest canceling a trough, is that okay? And it doesn't cancel it even up to 0, we can still classify as a destructive interference. Is that okay? In this term or in this consideration here. Are you okay, Sir Bismarck?
Yes, sir.
So it's good you observe that, because from what I've been teaching you is it's a canceling out to 0 that I've been teaching you. But in a question like this, we can also consider the fact that at least there's a cancellation somewhere going on as far as we have a crest and a trough, or we are talking about
Okay,
constructive
sir.
equation.
All right.
Okay, so the answer Sir George gave us is correct. For the A, we can see that they are all at the crest. For the B, you can see that we are just using this line to trace. You can see that they are all, one is at the crest, one is at the trough. So there will be a cancellation in one way or the other. The same way for the C, there will be a cancellation. The same way for the D, they are all at the trough end. So we are getting a constructive in that as such. Is that okay? Now, in terms of, in fact, this is not under films. This is under interference in general. The Michelson interferometer, that is also a very genius way that we can also observe the bright fringe to briefly. You see, there's a light source here, and I told you that if you want to observe interference in such a manner, we need a monochromatic light source. Yes, sir.
Yeah, please. In this the example that I had, so that do we have any partial interference? Does it exist in physics? Is there any concept like that?
If in general, yeah, if we are talking in the perspective of what we are doing, it's either constructive or destructive. But in the wider sense of learning in the application, we may get something like a partial interference. But that one's, I think we don't call it partial. I've forgotten the name we give to it. So interference may happen, but in our manner here, it's either we are getting a bright fringes or we are getting a no at all. Is that okay?
Okay. But in the example you give, you cited that you could say that there will not be any total distortion of their hand. So that's maybe the concept of partial will come in.
So in the concept of the question like so something like this, constructive happens, destructive do happens one way or the other. You see, when we are talking about their cancellation too is with a perspective. In as much as we need a bright light, we are not getting that exact bright light. It means there's something going on and it's reducing it. Is that okay? And from our phases that we learned, it's not only 180 phase of change that causes a total phase of change. They can be out of phase. They could even be 45 degrees. Is that okay? So something like this, supposing we had another waveform as big as this, and of course they have the same amplitude, that could have been perfect for what I have been trying to explain for the past hour. Is that okay? But as far as we have some calculation of crest and trough, we will still classify as a destructive and a constructive. Is that okay?
Okay. When there's a distraction in the amplitude, eventually, when there's a decrease in the amplitude, okay, all right. Thank you. Yeah.
So now, in under the Michelson interferometer, is also another important and an interesting way of also observing a dark fringes and a bright fringes. Is that okay? And this time around, you need a telescope to observe that. And we have a setup in our lab that we can use to do that. And I told you that this one too has a wide application. Interferometer is very, very wide. As of now, we have system that's based on this for even sample measurement and studies. Now we have a light source here. And if you remember, I told you for us to observe something like this, we need one, a coherent light source, and two, we need a monochromatic light source. And I've explained a coherent light source. It means they are all in phase, is that okay, traveling the same direction. And a monochromatic means it has only one wavelength. Please, it's important that you know this. If you don't see this question in section B, you will see it in section A. Is that okay? How interference should be observed. These two conditions are very, very important. Now, if we incident our light source in a mirror, and this mirror here, we call it a beam splitter. Beam splitter is going to just divide our light source into two for us. Is that okay? So let's trace the blue line here. Now we can see that right from the light source, we go to the mirror, which is our beam splitter. It divides it into two. So it divides it where one goes into this direction and let other half go straight into it. Is that okay? So one half is passing through it, one half is going opposite direction. Is that okay? Now, when it goes to this end, it hits a mirror. And now the mirror here is an adjustable mirror. When it goes to this end, that is through it, it hits a mirror too. But here, our mirror here is actually a fixed mirror. We expect that the mirror reflects the light that is coming. Of course, come to the mirror, the beam splitter here. And because the beam splitter has the ability to divide, it also has the ability to merge together. Is that okay? And this adjustable mirror also reflects it, comes to a beam splitter, and they all meet here, and there's an observer that is going to observe this with a telescope. Please hold on. Okay, yes. Yeah, sorry. So there's an observer here that is going to observe anything that is actually going to go on in here. Is that okay? With a telescope. Now, let's look at this. If it reaches the beam splitter in the mechanical principle point of view, we have a wave that is traveling. So our waveform is traveling. The same waveform here is traveling here. There's a P here that is going to serve as our second mirror or lens. And this one is just going to control the distance that is going to travel from here to travel from here. Because we want the distance from M here to mirror 1 should be the same distance from M here to mirror 2. Exactly. So we want this distance should be the same as this distance. Is that okay? And if that happens, the observer here will observe something we call a constructive interference. Is that okay? Because again, distance do matters in constructive and destructive interference. But immediately that we adjust the distance here using our mirror 2 here, you see that the phase will change with respect to the M2 here. Is that okay? So as far as the phase is changing, it means that we should be observing or we'll be getting a different form of what? Of an interference. And here, this time around, is going to be a destructive. Is that okay? Because one is causing other one to, of course, change. So here, the distance here is going to change the phase. And of course, this one is coming on its own way. Then the observer will observe a destructive. So in adjusting this mirror from here to here, the observer here can be observing something like a constructive interference and can be observing something like a destructive interference, which is very, very interesting. Now, I told you the application. Now, these applications are very interesting one way or the other because the reason why, because of how they behave, it's very easy for you to use a phenomenon like this to measure a very small displacement. I told you a colleague that we have the setup in our lab still. He used this wonderful principle to measure how burning a material burning level can reach. Is that okay? And you know, when you go to the standard authority, they put pressure on the material, and as the pressure is going, they increase the pressure, and that breaking point and the stress point and the strain point, they use to measure the modulo of elasticity and other things. This time around, his own can actually measure the very minute point of breakage. Is that okay? Because he was putting this one instead of the telescope here, it was a camera observing it. And I think he had a mirror here that is adjustable, and he had one board here that is going to represent his sample itself. And a pressure is actually giving it to it a little bit. Is that okay? And he was just moving this end and this end to observe what is going to go on when there's a light source coming here after reflection and what is going to go here. And he used a nice programming language to interface what is actually going to go there, to measure the small displacement of breakage that is going to go in the sample. Is that okay? So this principle can actually be used to measure very tiny movements or distances or displacement. Is that okay? In even to a point of a nanometer, which is very interesting. because this time around, our phase changes here that we are talking about is in nanometers. Is that okay? The wavelength that we are talking about is in nanometers. So if we can do this, it means it's very easy to measure a small displacement using this kind of a principle. And it's very precise too. Another typical application that we've been observing a lot are these things. Exactly. So I don't know if you've seen a peacock feathers before. That very nice brighten of colors. The color is not an inbuilt thing. It's a tiny layer that it has. In darkness, the color doesn't show. It shows when there's a light reflection on it. Is that okay? So light reflect on it. There are a lot of layers that it has in that feathers. And because of that, and depending on how thick these layers is and how the wavelength enters, because this time around we have white light entering, it emerges out with a very nice color pattern. Is that okay? And I told you that on rainy seasons, if there's a small oil on the floor, you see something too like this, which is very nice. And the normal bubble that I used to explain. Is that okay? So you see interference in our basic principle, and our basic principle, we observe it one way or the other. And even in the general performance view, we also apply it in the scientific world. Any questions so far?
Hello,
Should
sir.
I? Yes, sir.
This one, I will draw us back a bit, but then my internet went off, so I missed the session. Please, with the question that you posted, which ones were giving the constructive interferences and which one? I mean
Okay.
the ABCN.
So we have here the A, the D, the G, and the H as constructive, and the rest will be as destructive. So the one I've ticked, maybe you can take a screenshot. The one I ticked below here is a constructive. Is that okay?
Oh, okay.
And the one up, yeah, is a destructive. Okay.
All right, sir. Thank you very much, sir.
Okay. So if there's no question.
Okay, so
yes,
I have
sir.
a question. Yes.
Please do.
So, what is that thin line between interference and then dispersion of light? And then, so sometimes we confuse some of these things.
As a matter of fact, they are all dispersion. In fact, under interference, we get dispersion of light. But you see, dispersion of light comes in different principle and manner in their behavior. Exactly. In dispersion, we know that, of course, depending on which we'll be looking at very soon, depending on the refractive index like of the prism and how the materials bending behavior is, depending on their speed, we get a very nice emergent rays of light of different colors when the white light is passed through. In terms of the interference, it's still the same manner, but this time around, is very dependent on how the thickness of the thing is, like the thin film is, and also how light enters and the type of light that is actually emerging out. Is that okay? So the thickness is very important. The wavelength is very important. But and even as we go on, you will see that we have another principle as diffraction, which also brings something like a dispersion of light, which is also very interesting. Is that okay? Because I think what we all know is dispersion through, let's say, a prism, dispersion through, let's say, like a rainbow, droplet of water.
Yes.
But there are other ways that light can be dispersed. Is that okay? Okay. So, as of now, we are done with Unit 1 and Unit 2. We still have a lot to cover. So, for Unit 3, we are going to talk solely under dispersion. Is that okay? And we'll be basing our facts and everything on prism relatively. So we talk about normal dispersion, we talk about the angular dispersion, we talk about the anomalous dispersion, we talk about the effect that absorption actually have on dispersion. and we talk about the general perspective, the theory that we know under dispersion for now, and how even the nature and the vibrating of particles and even fraction also affect dispersion. Okay. So let's go straight to the point. So it's good, Sir Mike, Sir Bismarck brought this question. I was coming to talk about it. So dispersion, as we all know, mostly happens this way. Is that okay? So you see, if it's about to rain, it doesn't rain, and depending on where light is emerging out, you see a very nice colors in the sky. We call it the rainbow, which we've all done before. Is that okay? And if you remember rainbow, when we're talking about rainbow, we said we have a primary rainbow, a secondary rainbow, and it all depends on what actually happens in the droplet of water. Is that okay? So light enters, we have something called total internal reflection going on, we have refraction going on, we have reflection going on. Is that okay? Light emerges and you have a very nice pattern of colors, which is very, very important. Another thing is what we mostly know as using the glass prism. We use a white light, passes it through, and through after passing it through a prism, we have a very nice pattern of colors. And even Newton doubted this observation. He was saying that what if the prism is the one that is producing the light? It could be the light enters, it induces something in the prism, and it gives us this nice colors. So he brought another prism and turned it upside down to converge all the colors here. And interestingly, they all merged together and emerged out as white light. Is that okay? Before he was convinced that prism actually disperses light. Is that okay? So dispersion and from our old analysis and understanding, we know that if you have a shorter wavelength, it should be bending more, and a longer wavelength should be bending less. So when dispersion happens, we see that the shorter wavelength, like violet, is at the beneath here, and the longer wavelength, like red, is at the top here. Exactly. And yes, what was I explaining? So praise Newton's experiment on dispersion, bringing another one, and we get our white light image out. So these are all a revision. You cannot come to what you have to do. I'm just bringing your mind back to dispersion. Now, we also look at something called a dispersive power, where we related, if we have a prism, the prism has something like an angle in there, exactly, and it has also something we call the minimum deviation in there. We also looked at it with respect to the refractive index, and I'm sure we all remember still, because I think during atomic heat and optics, I taught this, where we have refractive index relating the sine into brackets, our angle plus the deviation divided by 2, sine of the angle divided by 2. And I think we also derived this formula where we had a property called the angular dispersion. Is that okay? And the angular dispersion is just the difference in the deviation between the extreme ends of colors. So if we are talking about red and the last one, violet, we want to know that angle between them, exactly. So the difference in their deviation, that is what we are interested in. So if we actually move more step, we can look at something we call the dispersive power, exactly. And that one actually relates the ratio of the angular dispersion, relating it between two wavelength colors, exactly. And of course, their mean wavelength, which we've done before. But it's still in the slides, so when I give the slides out, maybe you can still do a revision on it. There's a question here that you can try, which we will not go through. Now, the most important thing that we have to look at, something we call the angular dispersion. Exactly. So supposing we have a prism, and we have a prism where I'm coming. I have the parameters here. Let me define the parameters before. Okay. So we'll come back to this, but let's hold on to all the formulas here. Let's look at the prism at the top here. So if we have a prism here, and we have our angle alpha at the top here, then we have our another angle here, we have another angle here, and this distance between this end to this end is the path length inside, exactly. And there's an emergent ray that is actually coming out. This is my laser pointer. There's an emergent ray that is actually coming out here, exactly. And that range of distance that it can come out, we call it the width of the emergent beam, exactly. And of course, every prism has a base. So we're going to call the base here big B. I'm going back. If we have a dispersion, exactly. So dispersion is just separating of light into different components. It's very, very dependent on the refractive index and also dependent on something we call the wavelength, exactly. So depending on how the refractive index is of the material is, it will also affect the wavelength of the light sources, exactly. And of course, dependent on the dispersion. So if that is the case, it means that we can actually relate the change in theta over change in lambda, where this one represents our refractive index and our wavelength and our angle. And that is our angular dispersion, because angular dispersion is just talking about the range or that the very minimum light source emerges out compared to the very maximum or less bent ray image out, exactly. So we can represent it as change in theta. That is our angle here divided by the wavelength. So if we have this one as angular dispersion, of course, using differentiation, we can expatiate this one so that we bring in refractive index, because we are saying refractive index is very, very dependent on wavelength. And if we have something like this and we are opening differentiation, we can just do change in theta over change in n, multiplying the change in n over change in lambda. It's the same as this, because we cancel this thing out. You still get this whole thing. It's okay. So we just open it up. So now the first term here is just describing how emergent ray changes with refractive index. Exactly. And this term here is just talking about how refractive index changes with wavelength. Exactly. And our angular dispersion is this. Exactly. The way I'm moving, should I still go? Should I go?
Yes, sir.
Uh-huh. Now, if we have a situation like that, we can bring in Snell's law, when we are talking about, because refraction do happen, so we can bring in Snell's law to explain this. And the refraction that is happening here is not at this end. We are talking about what is emerging out here, the angular dispersion. The angular dispersion happens here. So if we are talking about the angular dispersion here, we can bring in Snell's law and relate it with the more dense medium exiting from the less dense medium. Is that okay? So if that is the case, we get n to be equals to sine I over sine r. We differentiate this and find the inverse. We're supposed to get our change in theta over change in n. That is the sine phi over sine theta. Is that okay? And here, our angle here actually represents the angle of incidence at this end. This is the angle of incidence. And here our angle here represents the angle of what? The emergent. Is that okay? So emergent ray is at this end, the angle of incidence is at this end. Is that okay? The same way, if we are representing this one directly, it means I here is going to be at this angle, and the R here is going to be at this angle. So here we can, of course, we represent this one as, maybe let me write, sine our phi over sine our angle here, that is theta. Is that okay? And the first thing that we have to do is to find the change in theta over n. And when you do that, we are just going to get the sine phi over cos what? Cos theta. Now, when we reach here, we are not done because we are talking about symmetry in terms of how the prism behaves. We can, of course, multiply 2 by the answer that we've gotten here. And because we can also have the prism in terms of how they behave. Let's say this one emerges out and we have one emergent coming here in terms of their mean. It means we can have the angle of this one. Then at the end, we will get our change in theta over change in n equals 2 sine into bracket the alpha divided by 2 over the cos theta. Is that okay? Now, we are not done still. If we have a situation like this that we have at the end here, and we want to relate the prism properties in relation with prism geometry, we can of course relate the angle, that is what we have here, the change in theta over change in L equals the base of the particular prism, and the B here is the what? Is the width of the emergent beam. Is okay. We can relate the two as this. And here, this is just representing the geometrical factor in terms of just prism geometry. Is okay. And we already derived this one at the beginning. Is okay. Which we can resubstitute what we have here as B over big B over big small b in here. Is okay. And just get this final answer. And this one is very simple because I wrote something beneath here so that you will appreciate that the dispersion in a medium happens because the refractive index depends on what wavelength. One, the total angular spread of the colors depends on both how strong the prism material disperses light. Is that okay? And that is what is represented about in this term. Is that okay? Because the refractive index is dependent on what? The wavelength. And the prism geometry. Is that okay? That is the base to aperture ratio, and that is what we have represented it here. Is that okay? So angular dispersion in general is actually relating the property of the material and also relating the prism geometry. Is that okay? Relating the property of the material in terms of how strong the prism is able to disperse light, and in terms of the geometry material. So if we have these two, in fact, we can actually determine the angular dispersion. Have I confused you enough, or we are following?
Sir, please take it again. Take that again, please.
Okay. So in the beginning, our whole goal was on this angular dispersion. Is that okay? This came along for us to relate it with different angles. Is that okay? And now we ended it here, where we are relating the angular dispersion, and we are relating it in terms of what goes in here when you are talking about angular dispersion. And in fact, if you are talking about angular dispersion, the material actually do matters. That is the prism. Is that okay? When you're talking about the material of the prism, we are talking about refractive index. Is that okay? Which is very, very dependent on the wavelength that is entering the material. And we are also talking about the physical geometry of the prism. Is that okay? So now, when you see the physical geometry of the prism, we're talking about the angles that it comes with, the base that it comes with, the distance that it has, and other things to emerge out and all. Is that okay? Which angular dispersion is very dependent on. So at the end, if we have this formula represented as the angular dispersion, we are saying that one, the dispersion in the material happens because of refractive index that is dependent on what? The wavelength. And the total angular spread of the colors depends on both how strong the prism disperses light, and that property is here. Is that okay? And in the next subsequent slides, we talk about something like the normal dispersion. We should talk about it later. And the last thing is, it's also dependent on what? On the prism geometry. Exactly. So the angular dispersion is very, very important and dependent on these two parameters. This first one is talking about the prism geometry. The second thing is talking about the material itself of the prism. Is that okay? So that is what angular dispersion is trying to talk about here. So if you want to know your angular dispersion and you know these two properties, it means you can determine your angular dispersion. Sana, if are you okay?
All right, say yes. Thank you. Thank you very much.
So I tried enough to also write everything here so that when you are reading to it will be convenient enough. Okay, so I brought a question here. The first question that I asked was, what is angular dispersion? And the second question that I asked is, if we have a base of this and we have a linear aperture of an emergent beam as this, what would be the rate of change in angle of emergence with the refractive index m? Do you want us to try this in 5 minutes, maybe?
Yes, sir.
Well, let's try this one, 5 minutes.
Hello, sir.
Okay, are we done?
Yes, I had with the calculation that talking of with that one, I had 1.21 rad
Okay,
because it's rad.
okay. Then in fact, this calculation, it will be dimensionless. You will not have any dimension for it, and we can't also relate it with angle per se. Is that okay? Because it's
Oh,
a ratio dependent thing that we are looking at.
okay. The way like
But
this is angular, so
yeah,
that's why
it's
like
very confusing. But the answer will just be represented as that. Is that okay?
okay. So,
The next thing that we also have to look at, can you tell us how you did it anyways before I move on?
okay. As we had the formula change in angular, is it change in theta over the change in the refractive index, which is equal to the base, the length of the base over the width of the emergence rays. Okay, so the capital B now becomes 7 centimeters, and then the width, which is the small b, becomes 5.8. So it will be B, capital B over small b, and that is 7 over 5.8, which will give you 1.21.
That's perfect. So we have 1.21. And the next thing that we have to do is we have to define what an angular dispersion is. And angular dispersion is just the change of angular or angle of emergence with respect to the wavelength. Is that okay? So that's what for the number one. So let me try and see if I can finish up with this section before we end the class. Is that okay? This is plenty. Okay. Okay, let me try. So we can also talk about something we call normal dispersion. Now, the dispersion variation we are looking at, we'll be looking at angular dispersion, we'll be looking at normal dispersion, we'll be looking at something we call anomalous dispersion. Yes, if I've not pronounced it, when you reach there, you pronounce it. So is that okay? Now, if we are talking about normal dispersion too is very, very dependent on refractive index and their wavelength. Is that okay? And if you are talking about it, we are just relating the change in the refractive index with respect to the change in wavelength. Is that okay? And we expect that for any normal dispersion, this is what happens. We have the refractive index to increase with respect to a decreasing wavelength. Is that okay? So anytime you have a material, the refractive index tends to increase. We should know that the wavelength of light that is passing through is also going to be what? Decrease. And it is because of this, that is why when we have a violet light, it tends to burn more as compared to a red light. Is that okay? Because this time around, if you have a refractive index, let's say, of increasing, and we have a wavelength, and a wavelength that is having a shorter wavelength means it has a smaller wavelength, it will burn more. Is that okay? And if it has a longer wavelength, it means the wavelength is high. Relatively, it means it will burn less. Is that okay? So that is why we have these two. So violet tends to burn more than that of the red when it passes through a prism. So relatively, we know that mathematically, as far as refractive index is increasing with decreasing wavelengths here, we should have our change in n over change in wavelength to be always to be what? 0. Sorry, less than 0. Is that okay? So we can't have a situation of say more than 0. Is that okay? It should always be less than what? 0. And less than 0, it means we are talking about what? Negatives. Is that okay? Now let's look at something here. So there are very key important factors that will actually happen before we get a normal dispersion happen. And one important thing is what I just explained. Increase in refractive index, of course, will decrease the rate. Another thing, this is just an example. I will bring the example illustration very in soon. Another thing that we also observe as a key feature to observe a normal dispersion is the rate of increase of if you have a slope of n versus lambda is greater at shorter wavelength. Exactly, which you'll be observing soon with an example. So I'll show you that one too. And there's another thing is every material behaves differently. It's very normal. Is that okay? So if you are saying the refractive index of water is say 1.33, we shouldn't be expecting it to be the same as a cloud or a quartz or anything. Is that okay? It's going to differ. And because of that, every material has its own curve. And the curve you're talking about is n, the refractive index plotted against wavelength. Now let me show you a chart here, which actually explains these features that we are talking about. So when you take, say, a clown glass, we take a dense flint, a light flint, a quartz, a diamond, water that is iced, we take a strontium, we take a metal, all these materials, they behave differently under different light sources. Is that okay? So we have a light sources and it's in Armstrong. Armstrong is 10 to the power 10 meters. Is that okay? It's 10 to the power negative 10 meters, sorry. So it's in Armstrong. So all units that you are seeing here is in Armstrong. Is that okay? So 4100 Armstrong, 4700 Armstrong, 5500 Armstrong, to the right 6600 Armstrong, right? Which is, we want to convert, it's still going to be say 140 nanometers or 470 nanometers. But here it's in Armstrong, so it's fine. Now, when you look at this one, as we start from the violet and going towards the red, it moves to a longer wavelength. Longer wavelength means we have high or greater wavelength, right? But you see, we are saying that anytime wavelength decreases, refractive index increases. Is that okay? So maybe let's look at in this perspective. Now, if you want to decrease, it means wavelength has to go this way. So it means we have high wavelength here. It's going down to violet. Is that okay? So wavelength is decreasing. Now let's consider only one material like the crown glass. And let's behave, these are their refractive indices. Let's behave their refractive indices at each of these wavelengths. So we are taking the first row. You can see that when we start from here, it also what reduces as it goes this way. Is that okay? But if we are following the path of the decrement of the wavelength, as the lambda here is reducing in this path, we go this same end for the refractive index n. We see that the refractive index will be also increasing. Is that okay? So you see we start from 1.7, 1.52, we goes a little higher, 1.5216. It goes a little higher again, 1.5225. It goes a little higher again, 1.5260. Is that okay? So this one is actually depicting these key features we are talking about, what? A normal dispersion. That anytime there's a decrement in wavelength, we should have an increment in what? In refractive index. And it doesn't behave only the same in only one material. In fact, all these materials, when observed under different wavelength, you get these properties. Is that okay? So wavelength decreases, refractive index also increases. Wavelength decreases, refractive index increases. Now, if like this too, let's look at this chart. Different materials, a telescope crown, there's another crown here which I can't pronounce the name, is borosilicate, barium flint, and vitreous quartz. And we have their refractive indices, no, their normal dispersion given. Now you know that normal dispersion, we're talking about the change in n over change in lambda, exactly. And we said that normal dispersion should always be less than what? 0. So we have our negative here. So these values beneath here are normal dispersion. We want to relate their normal dispersion with respect to their refractive index with respect to wavelength. We want to use to explain these key features of normal dispersion. Now we've established one fact, that wavelength decreases, refractive index increases. We are moving to the next one. The next one that we are going to talk about here is how different materials behave differently. And one, the rate change, the rate of increase of this slope that is being greater at shorter wavelength. Now let's look at something. If we have a change or a slope of n versus lambda, that is going to represent this. Exactly. We are finding slope, so change in n over change in lambda. Now we want to compare what we have down here with the wavelength. Now let's look at this wavelength. As this wavelength go down here, it reduces. Is that okay? It goes down, goes down, goes down, goes down. But this time around, when our normal dispersion here actually go down, it's this time around increases. So we see it in this manner. So we have it increase here, and we have this one decrease here. Is that okay? Which actually reflects on what the key feature here is saying, that anytime there's a rate increase in the slope of the n versus the lambda, we will have a greater what? The rate of increase is greater, we have a shorter wavelength. Is that okay? So as we are going and the normal dispersion is greater, we expect that there should be more what? Shorter wavelength. This is short. This wavelength is way shorter. Why can't I write? This wavelength is more shorter than the one that is at the up here. This is more greater than the one that is up here. Is that okay? And it behaves the same in all the materials. Is that okay? As we are going to the shorter wavelength, we expect that the change in the n over the change in the lambda should also be increasing. The borosilicate is increasing. The flint here is increasing. The quartz here is increasing. Is that okay? And interestingly, all these materials behave differently in terms of their refractive indices, in terms of their normal dispersion. They all behave differently. Is that okay? So these key features is very important in normal dispersion. The last thing that maybe we can look at is each material has its own curve. So if we take one material and we apply different wavelengths of light through it, and we measure the different refractive indices that we are going to get, this is how the curve, all the curves is going to behave. And you see here, we don't have a standard curve that it is also going to even behave. They all behave differently. Is that okay? But at least they are following one way, the other, a common path, but it's different. How fluorite will behave will be different from how quartz will behave. It will be different from how it will behave. Is that okay? And even under the crown glasses, how the telescope one will behave will be different from how the borosilicate will behave. Is that okay? All of them will behave differently. So it means all these features that it has been explained here is very important, and it's explainable. Is that okay? Experimentally, that okay, if I have a material, they all behave differently. Different materials behave differently, and different materials will have their own curve, one way or the other, with respect to the plot of a wavelength and a refractive index. And of course, if I have the increase in the slope or the change in n over change in lambda, it should be greater. It means that the wavelength is shorter. And the very last one, which we all know, that refractive index increases as wavelength increases. Decreases, sorry. Is that okay? So it's very, very important. Do we have a little time more?
No.
No, okay. So the next time we will meet, we will talk about still on the features, but we consider helium. Then we will look at the Cauchy's equation, which I'm sure those who are doing maths will have seen him a lot because he contributed a lot in, I think, differentiation and integration a lot. Then we also talk about, he proved something which at the end of the day wasn't totally, it was correct, but didn't fit all situations. So we'll look at his own perspective on the normal dispersion, come and talk there about the malus dispersion and from anomalous dispersion. I'm on board with RW, which built an experiment to prove that. And right after it, there's something that also disproved it. We'll talk about it. Then we also talk about some assumptions that Hot also did to prove the anomalous dispersion. They look at secondary waves. Then I think we will end with the continuous absorption and the discontinuous absorption. And that will be it for chapter unit 3 before we move to unit 4. Any questions so far?
But hello, sir, please, how much more minutes were you going to need for maybe an extension so we could see if it's
the rest of the slides, the rest of the units that is left, I'm not sure they are that much. So it's still fine. Today we just wasted 30 minutes. We didn't join early. If not that, I could have finished with this one. So
maybe
you don't.
the class that 30 minutes we can, maybe you could continue to compensate for it, or maybe I don't know what the others think.
If sincerely myself, I'm tired. You see the way I'm talking.
All right, sir.
Okay. So
okay, sir. Kindly make the slide available to us if you don't mind.
Yes, sir. Yes, sir. Very important.
Yes,
I'll do that.
Okay, all right. Thank you so much.
Have a nice day, everyone.
Sir, my brother will say last power. Is it last power for the continuation? They join late. I never join late. They wanted to go.
I
said, my brother, the one who said we should go.
You would extend the lesson. Do you know why I was late? They took our light last night, so it didn't come early. That's why.
So please, next week, let's join time so that we can finish early. If we're able to finish everything and we have more time, of course, we can go back and solve plenty questions. The questions are very important, but if we don't do that, always it's going to be a rush hour thing. Is that okay? So I beg the time we used to join, let's note that.
All right,
okay. So have it. Okay, you're welcome. Bye.
Bye.